ACCS. For this session, Professor Samar Hussain. Professor Hussain is an associate professor in the Department of Humanities and Social Sciences at IIT Delhi and is associated with the Cognitive Science program. His research examines the linguistic and cognitive processes that support language acquisition, comprehension, and production, with a particular focus on South Asian languages. His work draws on behavioral, corpus-based, and computational methods to study sentence processing, predictive and integrative mechanisms in comprehension, syntactic planning during production, and the influence of typology and cognitive factors such as memory, attention, and perception on language structure. I now invite the chair of this keynote session, Professor Niharika Singh from CBCS, to kindly take over the proceedings. Thank you.
Thank you, Sumini. So it's my pleasure to invite Dr. Samar Hussain to present his talk towards the typology of language processing. So looking forward to your talk.
All right. So good morning, everyone, and thank you for the invitation. I'm really happy to be here. So okay, thanks. Right. So if we look at our natural world, right, what we see is a world full of diversity, teeming with life of various kinds, right, and thankfully, in this case, we can ask what causes this variation, right? How can we understand this variation through some underlying mechanisms, right? Thankfully, in this case, we have an answer, right? And in the sense of a modern evolutionary theory, which can basically give some semblance of structure to this large variety that we have, which gives us, and you can basically divide this very sort of chaotic natural world into a very systematic structure, right? Now, it turns out, like the natural world, right, there are a lot of languages which are spoken around the world, and what we aim to do is basically to understand this variation from a variety of perspectives. And many of you might already know that, languages are related to each other, right? So for example, here is a cluster of language which is basically known as the Indo-European language. And on the top right, you basically see the Indic branch of this language family, right? And we know this because of certain historical work that has happened. In India, you will not be surprised to know, obviously, right, that there are over 600 languages spoken in this subcontinent. And most importantly, these languages actually belong to different language families. They're distinct language families, not just Indo-European languages, which is primarily spoken in the north of India. But you have Dravidian languages, which are spoken primarily in the south of India, but also Sino-Tibetan languages and Astro-Asiatic languages, right? And so India actually provides a unique opportunity to study language from a variety of perspectives. right? And in fact, not just about diversity, but if you were to actually look at just sheer numbers, right? In languages which are spoken in the Indian subcontinent are actually contribute to a large amount of sort of number in terms of numbers, the languages spoken by the world's population, right? So you have language like Hindi, Marathi, Bangla, Tamil, Telugu, right? And they're basically spoken by a large amount of people in the world. So it's important for us really to understand, right, how are these languages related to each other in terms of, in this talk, I'll be focusing on processing, right? So what can we think of processing when it comes to relationship between these languages? What is unique about processing in these languages? And also importantly, what are the universals that we can think of, right, when it comes to these different languages, right? So what are the universal cognitive constraints, and what kinds of processes are unique to specific languages, right? That's our attempt, really. So on the one hand, we can talk about certain universals which are potentially posited, which is that, well, there is some kind of a resource conservation given limited cognitive capacities, which will basically impinge on all the processing factors irrespective of which language you speak, right? There's also this idea of communicative efficiency, that we try and be efficient when we communicate. On the other hand, if you are a language which has subject, verb, object, word order, you might behave in a certain way. And if you are a word order which is subject, object, verb, you might actually behave in a certain way because of the nature of the language, right? So I want to start this sort of conversation here with this example, which is Ladki ne pehlwan ko pukara, right? This is a Hindi example, which basically translates as the girl called the wrestler. I've also written the sentence in Devanagari, right, for people who can actually read Devanagari. And I want to actually take this sentence and try and understand how we process this sentence, right, from two perspectives. From the perspective of comprehension, right, how we understand this sentence, and from the perspective of production, how we produce this sentence, right? So from a production perspective, if I were to speak this sentence, what are the different kinds of things I need to do very broadly? I need to do some pre-linguistic planning. I need to have some ideas to what I want to speak, right? And then I need to convert that pre-linguistic thought or structure, right? And then start doing some linguistic processing. And the first thing I might do is retrieve words. Right? I might do some lexical retrieval. And when I do that, then I need to do some structure planning. I need to arrange things in a certain order and then produce this sentence, very broadly speaking, right? And on the comprehension side, what I need to do, if I'm reading this sentence, let's say, right, I need to basically first decode scripts, right? Whatever symbols I'm seeing, I need to decode it. And then I need to do some lexical processing, right? I need to convert the symbols to sounds, then access the words which are there in my mental lexicon. Then I need to relate those words, and then hopefully I need to extract the meaning which was intended by the speaker, right? So this is basically broadly the two aspects that we would like to understand. So from a production perspective, right, I would like to focus on specific questions, right? So the first question would be, in this utterance which I'm planning, when is the verb planned? At what point in time I actually plan the verb, right? Before speaking the sentence, or at the point when I have to actually utter it? How is the word order planned? How do I go about planning this word order that I'm going to speak? And what is the overall scope of planning? Do I plan the entire sentence? Do I plan it piecemeal, which is incremental? So I'm going to basically try and give you some answers to these questions. through the research that we have been doing in my lab. From a comprehension perspective, what we can ask specifically, if I were to actually compute some kind of orthographic complexity, right, does that actually incur a cost while reading? When we think of words, right, are those words retrieved as a whole, or do we break them up and retrieve them? Right? When you think of these different case markers, right, which all languages which is spoken in the subcontinent have, things like ne and ko and per and se, what role do they play during comprehension? Right? How do they influence the upcoming verb that I'm yet to hear or read? Right? How do they influence, and how does word order influence all this? And finally, how much of this processing that I do is actually bottom up from the input that I'm getting, and how much of this information is top down, which is basically predictive in nature, right? Right? So let me give you a preview of what I'm going to actually be sort of arguing for, or at least trying to attempt to say that this is what we have found. Right? So what we are going to find is that in the production world, right, what you do is planning the verb in a very systematic or a differential way. Right? When you need the verb, because of certain kinds of grammatical constraints, you retrieve the verb early, right, before speaking. But if you don't need the verb because of other kinds of constructions, you plan the verb late. Right? So there's some kind of a differential planning that happens when we think about verb planning. The length of the phrase of the sentence, how large it is, influences the order in which it is placed, right? So argument length determines how you will place the subject, whether you will place the subject first or the object first, in how you basically go about arranging word order. And through this, what we find is a system which basically suggests that we have a clausal planning strategy, which is that before we speak, we actually plan the entire clause, right? On the comprehension side, what I'm going to show is that orthographic complexity actually, affects reading. So if you can compute the orthography and it's complex, then it takes you longer to read versus if it's easy. There's evidence now that we do some kind of morphological decomposition in languages such as Malayalam and Bangla, which is that you break up the words while you read. And that during processing or comprehension, you use these different case markers to actually predict the upcoming word, the upcoming verb specifically. And also interestingly, what we'll see is that when I predict the verb, right, if this pre-verbal environment becomes complex, my prediction suffers. Right? It's not always infallible. And finally, the evidence that we do both of these things together. We do top-down processing and we do bottom-up processing together. So that's my talk really, and I hope that I can, tell you everything in time. Right? All right. So let's start with scripts, right? And all of you will actually know that there are different kinds of scripts in the world, and they can be organized in a variety of ways, right? So, for example, there are different parameters in which you can actually split the properties of these scripts, right? So there's one very important aspect which is what is called as a grapheme sound mapping, right? The symbols, right, have to map to certain sounds, and this mapping varies across different scripts in the world. Right? In English, which is alphabetic, right, you have consonants and vowels appearing as alphabets, distinct alphabets, right? So you have things like cat versus cut, where you have the two vowels represented as specific alphabets. You also have differences based on grapheme forms, right? The symbol might change. In English, for example, you have the uppercase and the lowercase, right? They have different forms, but it's the same symbol, really. Directionality differs. So some languages are written from left to right, some languages are written from right to left. There are also languages which are actually, horizontal, have a horizontal axis. and so on. And word boundaries, right? So we tend to, in the subcontinent, many of the languages that we speak are separated out via white spaces, but that is not necessarily true. There are languages which basically have scripts where white spaces are not there, right? There's no word boundaries. So all of this basically gives you a sense of different scripts, and what we did basically with Devanagari, right, which is basically has a property which are called abugidas, right? And it's a shallow script where the mapping between the sound and the symbol is quite transparent, but it also has non-linear properties, right? Where different kinds of sounds, vowels, appears at different positions in the scripts, right? It could be top, it could be bottom, it could be left, it could be right. That gives you a sense, that gives a nature which is non-linear, right, to the script. And the graphemes also change depending on various contexts, right? In this context, so if you have a consonant such as gh, right, and if the inherent vowel which is missing, which is shwa, right, the shape changes, right, becomes different. There are also different kinds of ways in which you can, if you have a like sh, right, which comprises of different sounds, then the symbol is very different. Tra is very different, right, compared to ta and ra. All these properties are there. So what we did was we basically came up with an orthographic complexity metric, right, where we basically said, all right, we're going to try and capture some of these properties. If the vowels appear to the left of a consonant, I'll give a specific cost. If a diacritic is appearing below a consonant, I'll give it a cost, and so on, right? If the consonant appears without an inherent vowel, then I'll give a cost. Because all of these basically lead the script to go away from a transparent sort of mapping in linearity, right? And what we find, right, so for example, a word like din, right, will have a cost of 1 because, well, it has a vowel, the short vowel e, which appears before the consonant, but is actually pronounced after the consonant, right? You say di, you don't say id, right? But you write it as id, but you pronounce it as di, right? So there is an asymmetry between how you write and what you speak. So there is a cost for that, right? And similarly for other kinds of words. So what we did was basically we ran a eye tracking study where people basically read sentences. And then we know, for example, there are two very easy to understand effects. One is the effect of word length, right? Which is that if a word is long, right, you take more time to read those words, and if a word is short, then you basically are faster at reading those words, right? Now, what we find is that orthographic complexity interacts with word order, right? Such that the problem that you face with longer word orders increases when the orthographic complexity is more versus when it's short, right? Similarly, right? So similarly, word frequency is known to affect reading time. So if a frequency of a word is very high, which basically means it occurs in your vocabulary at a higher frequency, then you take faster, if you take less time to read the word. And what we find again is that that word orthographic complexity interacts with word frequency, right? Such that the effect, the faster reading time that you get for frequent words, they get attenuated with more complex orthographic words, right? So orthographic complexity interacts with both word length and word frequency in this interesting way, right? So let's say now you have somehow basically decoded the script, right? You now have access to the word with some difficulty. Now you need to retrieve the word, right? You know what the symbol is, now you need to retrieve the word. The question that we can ask is, well, do you take this entire word and retrieve it from your mental lexicon, or do you need to break it up into smaller subunits in order to get this access successfully, right? So for example, if you have a word like, if you have a word like eats, let's say, do you get the word eats as a whole, or do you break it into eat plus s and then basically retrieve this word? In Hindi, if you have a word like pukara, let's say, right, do you retrieve pukara, or do you retrieve pukar plus a, and then you combine it, right? And so in Malayalam, or for example in Bangla, all these languages will have these kinds of properties, right? I'm going to not, all I will say is that, well, there is evidence, right, for this smaller subunits, right? And we'll just have to wait for Nayana's talk in the next session to see the evidence for this, right? That all I can say is that, well, we have evidence that this in fact is broken up during lexical retrieval, right? You don't do whole word retrieval, you break it up. All right. So now with lexical words, the next thing that I need to do is I need to now relate two words together to start getting meaning out of the sentence. So I have retrieved, let's say, ladki ne, and I have, let's say, I'll retrieve pukara somewhere. But in order for me to make sense of this utterance, I need to now relate these two words somehow, right, and make sense of this sentence. And this process structurally is what is called as some kind of a dependency resolution, right? So there's a dependency between two words, and you're resolving that dependency. And so the idea in SOV language, because of its nature, in the literature is that, oh, you know, one of the key things that happens in these languages is because the verb comes at the very end, you start anticipating the verb based on the information that you get before the verb arrives, right? So the dependent, for example, ladki ne, predicts the upcoming verb. And then all this intervening element that you have makes this prediction more precise because you have more information now, right? And then when the verb eventually arrives, this prediction is very nicely maintained, and therefore you see facilitation in the verb, right? Because, well, you've basically made the prediction well, maintained it, and now when you get the verb, you say, well, I know this verb, I've already predicted this verb, right? So there's facilitation. And so this is the story that is basically there in the literature, and I'm going to basically make this story complicated, really, right? So there are two key effects that we would like to sort of keep in mind in this context. One is what is called as the anti-locality effect, which was first observed in German. It's 25 years ago now. So this is self-paced reading, basically, where people press buttons and one word appears on the screen at a time, and basically you can read the sentence one word at a time. And these button presses are basically being recorded, and they basically reflect your reading time. And what was found is that as the verb, in this case, which is in bold, goes away from its argument, right, in sentences 2, 3, and 4, the reading time at the main verb, which is gelegt versus hingelegt, becomes less. It becomes faster, right? Which goes against the idea of locality, which is that, well, you should be better when things are closer to each other because of memory considerations, right? What you got was faster reading time, right? And this faster reading time was given the name of anti-locality effect, that in a language where the verb appears at the end, you can make good predictions, and because of those predictions, you get facilitation in the verb. So this is one very important effect that we would like to keep in mind. The other important effect that is relevant for us is what is called as forgetting or no forgetting, right? So these sentences, right, are called center-embedded structures because you have a clause within a clause, right? So you have a main clause which is the rat escaped, but you have another clause within the clause which basically says the cat chased, right? So the rat, the cat chased, escaped. And you might say, oh, this is, well, not so good, but it is okay, you know, and fine, but I can, I can make this more complicated, and suddenly you realize, well, it's a very difficult sentence, right? These are notoriously difficult to process. These are doubly center embedded structures, known to be difficult from a very long time ago, right? So now, what people have found, right, that in English, if you were to actually give this sentence, people, well, do not do good, right, in trying to process these sentences. Specifically, so notice that these kinds of structures have a schematic of N1, N2, N3, and then V3, V2, V1. There are 3 nouns and 3 verbs. And what they found is that if you were to actually take away one verb, which is V2 verb, and ask people to rate these sentences, English native speakers, right, they rate this ungrammatical sentence equally well as the grammatical counterpart, which basically means that they are, well, not doing a good job at understanding what is happening, right? There's what is called as forgetting, right, of the verb. Well, interestingly, again in German, people found that you don't find this effect in German, right? If you were to actually get German speakers to read these kinds of sentences in German, right, then they get tripped at V1 because they say, oh, well, wait, I didn't see my V2, right? So they basically, they figure out there's something wrong with the structure. And the explanation was that, well, in German, because German is a V2 language, right, where you actually have a verb final structure, your parser has become very good at parsing these structures and maintaining these kinds of structures, so you don't mess up the parse. In English, verb final structures are very rare, right, and therefore your parser is not good. So both antilocality and so-called no forgetting is an important property that has been attributed to parsing in SOV languages, right? So we'll keep these 2 effects in mind before we go to what we want to quickly discuss, right? So in Hindi, right, does prediction happen? The answer is yes, the prediction happens. So this is an illustration of such kind of a prediction. So in this 5A, you have some kind of a relative clause, such as जिसने किताब बहुत दिलचस्पी से पढ़ी थी. The critical verb is पढ़ी थी, which is the read. And what you find is that if you were to compare the reading time at पढ़ी थी in 5A compared to 5B, where you have, rather than किताब पढ़ी थी, you have पढ़ी थी किताब, the verb appears in a non-canonical order, suddenly there is an increase in reading time, right? And so the idea is that, well, I see a jisne with a ne, and you know now that I'm going to basically be getting a transitive verb of a certain kind in a certain word order. And if I don't get it, I'm surprised, right? And this can be easily explained using some kind of a expectation-based account. So does prediction happen in a language like Hindi? The answer is yes, it does, right? Now, we can now take this forward and say, okay, now you predict verbs, but do you also predict suffixes, right? Do you predict parts of verbs, right? And so we did this in Malayalam, right? And we find that indeed, right, people can in fact predict aspects of the verb. So in this case, this suffix which is there. And more importantly, the effect that you get for facilitation at the verb is only because of the suffix, independent of the facilitation that you see because of the verb. So the idea is that, you predict the verb, but you can also predict parts of verbs in a language like Malayalam, right, where morphology is very, very rich, right? So there's an independent facilitatory effect due to suffix prediction, right? Irrespective of what you do with the verb, you also predict the suffix, which is pretty cool, right? So what we have tried to establish in these 2 slides is that prediction is happening in the languages both at the level of verbs and at the level of morphology. The question that we would like to ask is basically, of course, not to contest that prediction is happening or not happening, but what are the limits to these predictions? Where does this prediction break down is the question, right? Is the story very neat and nice, right? So for that, what we did, we started systematically conducting these sentence completion studies, where we manipulated different pre-verbal nouns, right? One noun or two noun or three noun with different case markers, right? So for example, you have a sentence like Pooja ne Urmila ko Sunit se, and or Pooja ne Urmila se Sunit ko, and all those different kinds of combinations. When there were two verbs, when there were one noun, or when there were two nouns, or when there were three nouns, right? And what we find, when you were to actually see how much grammatical completions are happening, so these are incomplete sentences and people have to complete the sentence, right? This is also not timed, so you have a lot of time to actually finish, right? What we find is that the ungrammatical predictions for one or two verbs, noun conditions is less, right? But as soon as you get to the 3 NP condition, the ungrammaticality increases, which is like, right? So then, what people do really is when they predict, they actually predict simple rather than complex, right? They avoid certain kinds of structures which are known to be complex, right? So for example, they will probably avoid predicting a lot of embeddings, right? They will rather predict a simple clause rather than embedding. And in order to appreciate this, I would like you to sort of, bear with me these certain structures. If you were to think about these 3 nouns and ask yourself, what are the different ways in which you can complete these nouns, the N1, N2, N3, in your own language, what you will realize that you can actually complete these sentences in a variety of ways. You can either use what are called as causative verbs, right, where somebody is making somebody do something, which are not simple, they are morphologically complex. Or you need to posit two verbs, right? So, bolne ko kaha or some such. Or you need to predict 3 verbs, right? So these kinds of 3 NP conditions can be predicted in a variety of ways, and you can measure what complexity arises when you predict different kinds of continuations, right? So I've also added how many verbs are you predicting, how many different kinds of dependency relations need to be established in order for you to predict those kinds of completions. And what we realize is that typically what you predict is simple rather than complex, right? That's the norm. The mistakes that you do are also very interesting, right? So if you were to actually make a mistake with the 3 NP condition, many times you forget, you ignore the first noun, and you use the last 2 nouns and make predictions, right? So you will say, well, and somebody ne somebody ko introduce kiya, and you forget the say, right? So these mistakes are also systematic. What this tells you is that prediction falters, right? Now remember, one of the key claims about anti-locality was that, well, as you increase the distance, prediction should become better, right? So what we try to do is we introduce different kinds of modifiers or linguistic elements after these 3 nouns to see what happens to these predictions, right? So added distance. So this was a baseline condition which we have just seen, but you can add things like kal der sham mein or something like, right? Yesterday late evening, or add some other kind of linguistic material related to a relative clause, and so on. So we added a variety of additional material after these 3 NPs to see what happens to the predictions which were made when nothing was added. And what you find is that invariably when you add some more material, the ungrammatical predictions increases rather than it becoming better, right? Which basically means your prediction system or your parsing system is suffering, right? Which is already under strain, and I've added more complex or more material, and you're basically sort of kind of struggling now, right? And so the ungrammatical completions under conditions where you increase the distance was close to 42%, which is pretty high, right? Which basically means people are not able to handle these kinds of sentences, Fine. So, quick takeaways. Um, what we find is that prediction suffers with increased pre-verbal complexity, and that predictions are simple rather than complex. This is what I've been trying to sort of show you in these slides. So what is the implication for anti-locality effect, which we just discussed, right? What do we make of the anti-locality effect? So we try to replicate, in the light of these kinds of studies that I've shown, we try to replicate previous experiments in Hindi which had showed anti-locality effect, and what we find is that you do get facilitatory effects at the verb, that effect you get, but if you were to compare those effects with closed task, which is what people predict, and if you were to actually ask people comprehension question in the experiment, then you realize that this reaction time does not align with the prediction scores and the comprehension scores, right? Which basically means, right, so either we were not able to replicate, but if we were able to replicate, then this does not align with the comprehension accuracy and the completion data, which suggests that at the very least, the claim can be that the facilitation is not because of robust prediction, right? You can attribute it to some kind of a shallow parsing strategy, that people are doing something, but they're not actually doing prediction and integrating the structures that you want them to integrate. What about forgetting that we discussed? Do Hindi native speakers forget what they have predicted, right? And the answer is yes, they do, right? So we did this this manipulation that I showed you, where what we did was that we took the object of a verb inside a relative clause. So for example, you say, kitab, dilchaspi se kitab padhi thi, rather than saying that, you say, dilchaspi se padhi thi kitab. You take the object and place it after the verb, and then there is some material after that which is not related to the relative clause. It's actually related to the main verb, but people use that and just form a parse, right? So, for example, they'll say, they'll make a parse something like, that boy who read book, fat was, this is an ungrammatical sentence because the fat is feminine, right? But they will take the book and basically combine it with the material which does not align with book, and be okay with it, right? This is reflected in both reading time and accuracy data, right? They'll say, oh, was the book thick, right? They say, yeah, the book was thick, you know. But you should not be making those kinds of parses because, well, the book does not belong to that kind of linguistic utterance, right? So you find these very interesting things which basically suggest that the anti-locality effect that has been reported and attributed to robust prediction is not driven by prediction. And you can, in fact, have structural forgetting, or this prediction that you're making is fallible, right? And what we have argued is that this prediction mechanism is actually constrained by your limited working memory, and it's basically subservient to that. You know, you cannot assume that the prediction mechanism will be all okay in these kinds of constraining environments. So what we then did, I'll just be quick here, what we then did is that we tried to see whether these predictions that people are making can get a nudge because of priming, right? Because priming is also, there's something called syntactic priming, which basically has been shown to occur cross-linguistically. So can we prime a complex structure is what we asked, right? And the quick answer is, so what we did is we compared priming transitive structures, which are simple, versus two argument structures, two argument causatives, and then comparing ditransitives with three argument causatives. So causatives are deemed to be difficult verbs, and these transitives and ditransitives are deemed to be simpler verbs, right? So when we try and see if, so you say, okay, what happened is a no prime condition, and you have the transitive prime or a causative prime, and then you have a target, which is basically you need to complete these sentences given the prime. And what you find is, in spite of a complex prime, right, people still prefer to predict a simpler structure, right? Which means that the priming mechanism is not able to override the default propensity of the parser to go simple, right? The parser wants to predict simple stuff, right? And it just ignores the prime if it's complex, right? Overall, what we have found is that so this is a summary of whatever I've said so far for comprehension. There is a tangible cost at the lexical level, both at script, depending on the script type, and morphology. When we think about prediction in SOV languages, the evidence that we have is that you predict simple rather than complex. This tendency to make predictions which are simple is not overridden by syntactic priming. And so we need to better circumscribe what is the role of priming and prediction in these languages. They are basically constrained by certain other cognitive constraints which can be deemed universal, right? That irrespective of languages, your prediction is going to be constrained. And it's basically because, well, you have limited capacity. All right. So now we move from the comprehension world, and quickly, I have 5-10 minutes, right? Yeah? Okay, so very quickly to the production world, right? So now I basically take the same utterance, right? If you have this figure, right? And I need to basically produce this sentence, right? So I need to basically say, Ladki ne pehlwan ko pukara, right? I give you this figure and you need to produce this sentence. How do you proceed, right? The idea is that you conceptualize, okay, this is what I want to do. Then you do some linguistic formulation, right? And then you articulate, right? And within this linguistic formulation, there are two kinds of things that you can do. One is that you can do some kind of functional processing, and then you can also do some kind of positional processing, right? And functional processing would mean, oh, who is doing what to what, right? How are these things related in the sentence that I'm uttering? And then positional processing would be, all right, now that I've established who is doing what role, how do I arrange these things when I produce the sentence, right? So let's talk about functional processing, and we can think about planning of verbs, right? And so there are different ways in which people have argued for planning of verbs. One idea is that, well, you plan the verb early always, and therefore you have some structure. The other idea is that, well, you plan the verb only when it is about to be articulated, right? These are the two sort of broad ideas. And what we were trying to get at is that we said, well, you will plan the verb strategically. In a sense, when the subject, right, requires the verb, you will plan it. But when the subject does not require a verb, right, then you will not plan it, right? So it's not either or, right? Within a language, you can have different planning strategies depending on the linguistic construction that you're uttering. And in Hindi, it turns out that there is this very interesting property with ne, which only occurs with a certain kinds of verbs, right? And if the verb type is not that, then you don't need ne, right? So the idea was that if there is a perfective aspect at the verb, then you will need ne, right? And therefore you will need the verb, and therefore you need to plan it early. But if you're not producing ne, if it's an imperfective aspect that you're producing, which requires a different kind of a case, then you can rely on the conceptual message, right? Which does not require any linguistic planning. And therefore, you don't need to do any planning for the verb. And therefore, you can start planning the verb when it is needed, right? And we did an eye tracking study with visual world paradigm to basically see how does the eye movement pattern change based on the timing of your speech, right? And this is a very quick snapshot right? And I'm just going to jump to the results after this. The idea is that in the first 400 milliseconds, what you actually do is some kind of a gist apprehension, which is you try and compute the conceptual message, who is doing what to whom, right? And in that scenario, for both perfective and progressive, you will do some planning which is at the conceptual level. You don't require any linguistic formulation at this stage. But before the subject, from 400 milliseconds to the time when you are about to speak the subject, you will need the verb in the perfective condition because, well, you can't say the verb. You cannot plan the ne without the verb. So you will retrieve the verb. But in the case of the progressive case where there is no ne, you will just plan the subject and just go ahead. You don't need the verb. From the subject onset to the object onset, right? In the perfective case, you will plan the object because, well, you need to speak the object. In the progressive case, one option which is being proposed is that, well, before you plan the object, you also need the verb. So there's some other proposal. So that could happen. And finally, before the verb, in the perfective case, you will not do anything because, well, you've already planned the verb. Everything is fine. And in the progressive case, you might plan the verb, right? So depending on the construction, right, you will do different things in your planning strategy, right? And so this is a scary picture, but this is these are the kinds of sentences, pictures which were shown, and then people had to basically look at these sentences and produce look at these pictures and produce sentences while their eyes were being tracked. Right, so this is a very quick snapshot of the eye movement data. And I don't think I have the time to give you the details, but what we find broadly is that you find evidence for differential planning. Right? That eye movement pattern in the first 400 milliseconds is identical, which basically means conceptual planning is happening for both perfective and progressive. But after that, you have very differential eye movement pattern for perfective versus progressive, right? Suggesting that in the perfective case, you're actually deriving the verb, whereas in the progressive case, you're not, right? So, I'm going to skip all the details, all right? What do we find? We basically find that you plan differentially, strategically. If you need the verb because of certain grammatical constructions, you will get the verb, plan the verb. But if you don't, then you will basically plan the verb late, right? All right. So let me just quickly, right, talk about word order. And there are basically, you can ask yourself, well, why do you have different kinds of word orders, right? Why do you shift, right? Why do you take the object and say object, subject, verb, rather than subject, object, verb? And the idea is that, well, one way to think about it is that, well, you plan the easy things first. So if something is short, you say it first, right? That's one idea, right? So you plan short words early, late words are complex, and long words are complex, therefore they're planned late, right? The other idea is that, well, if a noun is very long, it becomes conceptually very salient, and therefore it's easy to plan. These are all competing hypotheses, right? And the final argument is that, well, you arrange word order in such a way that you place nouns and verbs close to each other, which is what is called as a dependency length minimization hypothesis, right? You plan it in such a way that verbs and nouns are close to each other, right? So these were the three different ways of basically of word ordering that we were actually investigating. And what we find is that if you have a choice between these kinds of orders, where you have SOV, where the O is very long, right? The object is very long because of a relative clause, you find evidence for dependency length minimization, that people try and speak the sentence such that the overall dependency length is maximized, or rather minimized, such that you would rather speak a sentence like SOV and then you take the long RC and place it at the end. Right? That's what you basically do. Rather than doing OSV, ORC, SV order. Right? So you basically say something like, Pari ne bachcho ko behlaya, jo subah se ro rahi thi, or something. You take that entire big thing and place it at the end. And when it comes to easy first or DLM, what we find is that there's evidence for both dependency length minimization as well as easy first. So you do both, right? All right. So let me wrap it up, right? So when we think of parsing or comprehension in SOV languages, what we find is that it is basically an interplay of both bottom-up and top-down processing. The idea is that you take the linguistic representation, you store it in memory temporarily, it will degrade or it will get distorted. Because of this distorted linguistic representation, you will make certain predictions which can go incorrect, right? They'll be fallible. And then you will retrieve all these elements which you have actually encountered, and these retrieval processes will also be fallible. So your predictions will be difficult, can be difficult, and your integration can be difficult, right? This kind of a mechanism will lead to predictions which are simple and can also lead to forgetting, right? Where things are actually not getting integrated properly, right? And we said that, well, priming helps, but it cannot override this overall tendency of the parser to go simple. From a production perspective, what we find is that verbs are planned differentially depending on the linguistic reality of your language. If you need the verb, verbs will be planned early. If you don't need the verbs will be planned late. We find that both easy first as well as dependency locality are at play for word order. So Hindi native speakers at least are opting for two kinds of efficiencies. One is what can be deemed as lexical efficiency. Okay, I'll plan the verb which are items which are easy, but I also care for structural efficiency, where I want to relate two words together, because if I don't, then I might falter in my speech. I might say things which are not fluent, right? All right, so what we are arguing is that if you were to build a sort of a profile of a language, you need to consider two broad things. One is language dependent, so you need to know what is the nature of the script, what is the morphological properties of your language, what are the salient properties in your language such as word order, case markers, agreement. You need to care for them. And then you need to see how are these properties interacting with things that can be deemed language independent and universal. Things such as properties of retrievals and encoding in working memory, attention, what are the different kinds of prediction and heuristics that we make, and things about communicative efficiency. And when you combine these two things together, you basically get an overall picture of how a language will be processed. Right. All right, thank you. All this work, most of the stuff that we do is basically supported by DST. So I'm really grateful to DST, and thanks to the lab, my lab members at the Psycholinguistics lab at IIT Delhi. These are the people who have basically helped through the work. Ishita is a current graduate student who has worked on aspects of the bottom-up, top-down processing. Nayana is the person who is basically doing all the lexical processing work. Pranab is working on agreement. He's basically, and then Mudafia is the person who's done all the production stuff. Wasim did the priming stuff, and Apurv basically did the first set of prediction studies. And then Sakshi is faculty at DU. She worked with me on the forgetting bit. And then there's Himanshu, who is at IIT Kanpur. He's basically been involved with my lab for a long time, but more recently with modeling the top-down and bottom-up aspects of sentence processing. All right. So thank you.
One or two questions?
You can, I think you can just turn it off and this, yeah.
Okay, so slightly different question. One of my pet peeves is that so much work is based on reading, right? And what about auditory comprehension? Now it's going to have constraints which are different even from self-paced reading. So do you think your results will generalize smoothly to auditory comprehension, say in Hindi?
The kind of stuff that I've discussed today, we are trying to do it in a naturalistic Hindi dialogue corpus, right? So we are now trying to see how Hindi speakers and listeners engage in. I think this is not. During naturalistic dialogue. So I think that's very important. That's the next step, yes, absolutely. इसको छोड़ दीजिए, मैं बात कर.
I think this.
It's okay, I can talk now.
that inform planning, right? That do they have any backward effect on how you assemble it? Or is this independent of how this muscle system works?
No, that's a very good question. So all I can say is that I will not talk about the motor sort of planning. I think that's a very fascinating part. What we are trying to do right now, the extent that we are going using the dialogue stuff, is to see the feedback or monitoring that happens because of my errors, my hesitation, and the kinds of things that so my own monitoring of my speech, how does that impact planning, right?
Yeah, and also the planning of meta-linguistics,
Yes.
to modulate.
Yes, absolutely. Yeah, absolutely. So those are things which we haven't looked at. Somebody has to look at, yes, completely, yes. But I'm sure that motor planning, in fact, not just during speech, I can also think about motor planning constraints informing writing, when you type, right? There's a lot of interesting things that can be done during production. The motor memory, right, will have some interaction with the production system. So I think those are things which needs to be done, but we haven't.
The other question is that there are other typologies in a smaller context. For example, Calvin's typology or verb typology, how we pack information, and it seems to be different in different languages. Would this also have an implication of how the cognitive system, right, interacts with this? There's a bidirectional, I guess, interaction between how the language gives facility, how the cognitive system adapts to that.
Yeah. No, I think that's a very important point. The cut that I am making in this talk is one way in which you can actually think about typology. So surely, when you think about cognitive linguistics, you can imagine that, for example, if you have a verb frame language versus a satellite frame language, you could imagine that, when I perceive a image, right, then such and such language speakers will perceive it in a certain way because of the event ontology, so to say, right, in their mental sort of framework versus some other, and that will have implication on planning. I think we should do that. Yeah, it's a very good point. But we haven't, yeah.
Thank you so much for such an interesting talk.
अभी 2 मिनट के रुको, ऐसे नहीं जल्दबाजी करनी है. हेलो. हैंड माइक
Thank you, Professor Hussain, for your wonderful talk. I now request Professor Niharika to kindly present the memento to Professor Hussain. Thank you. Thank you, professors. I now request Professor Ark Verma from IIT Kanpur, the chair for the oral session on language and cognition, to please take over the proceedings. Thank you.
Okay, so thank you so much for the fascinating talk. We'll move on to the first oral session of the day. The session is titled Language
Hi everyone. So I'm Gorja from IIT Gandhinagar, and I'll be talking about number feature and noun distortion in Hindi sentence comprehension. So if you all consider the sentence, school में शिक्षक ने छात्र को किताब से पढ़ाया था, which translates to the teacher taught the student using a book in the school. So to understand this sentence, you have to figure out who did what to whom. And this figuring out happens incrementally. You build this interpretation incrementally. What I am interested in looking is at what cognitive processes underlie this sentence comprehension procedure. So working memory plays an important role in sentence comprehension. So readers need to maintain, retrieve and integrate linguistic chunks when they read a sentence. So again, in this sentence, school में शिक्षक ने छात्र को. So as you go reading the sentence, you have to maintain the initial linguistic input. And then at the verb, you retrieve the previous input that you saw. And then at the end, integrate it to make sense of the sentence. Now, cue-based retrieval is one working memory-based model. This model says that real-time sentence comprehension is driven by a content addressable search in the memory. So what this means is, in a sentence like this, at the verb padhaya tha, there's cues generated for what kind of argument that verb will take. For example, in this sentence, this requires a subject noun which should be singular. So it sends these cues and this activates noun phrases. So the actual subject noun, which is singular, completely gets retrieved, but also a distracting noun, a second noun, which partially matches the cues, may also get partially activated. One major assumption of this model is that it claims that the memory representation of the linguistic input stays completely intact and it is retrievable as is. A new proposal is representation distortion. Representation distortion says that the sentence material that is stored in the memory probabilistically distorts to a non-veridical representation, and this distortion can occur due to deletion, insertion or feature misbinding errors. So in a sentence like this, which is an ungrammatical sentence, so शिक्षक को छात्र को किताब से पढ़ाया था, we might distort it to automatically read it correctly as शिक्षक ने छात्र को. So this claim has been shown to occur in English and Russian via the feature percolation theory, which says features of a distracting noun can percolate to a previous noun to make an ungrammatical sentence seem grammatical. And in Hindi as well, in the case of case marker distortion, which the example shows. Now the theoretical importance of representation distortion is that it gives a completely new theory of how working memory is involved in sentence comprehension. And additionally, it also aligns with the visual processing literature, which talks about feature misbinding. Now, it lacks testing using well-controlled experiments, and what kind of distortions occur in the memory has not been looked into greatly. So that's what we look to do. We test it in Hindi because Hindi is an important test case. It is a rich case marking language which can cause confusability, and it can also cause more feature binding errors. Also, working memory effects, which are usually well attested in English, might not show up in Hindi as well. So we tested in Hindi. So the present study involved two sub-experiments, the noun distortion and the number feature distortion experiment in Hindi. So the question was, does representation distortion occur in Hindi? And what are the kinds of distortions that occur when pre-verbal nouns might undergo distortion to complete argument-verb dependencies? So we used an acceptability judgment study. The participants were given a self-paced reading task of Hindi sentences, and they were asked to rate them on a scale. So the first experiment is the number feature distortion experiment. Here we hypothesize that in a sentence like वो अच्छे शिक्षक छात्र को किताब से पढ़ा रहा था, where there's a mismatch between the noun phrase, the subject noun phrase and the verb phrase, the participants might automatically distort this as वो अच्छा शिक्षक छात्र को किताब से पढ़ा रहा था, perceiving it as grammatical and thus rating it highly. So these were the conditions in the experiment. They had different combinations of matches and mismatches between a subject noun, a distractor noun, and the verb. There were 2 grammatical conditions and the rest were ungrammatical conditions. So we predicted the results based on 4 models. The first was the Q-based retrieval model, as I described before, and the other 3 were representation distortion models. The first one being plural feature insertion on first noun phrase when the second noun is plural, the distracted noun is plural. We call this the swap error model. The second model was the plural feature insertion on the first noun phrase. We call this the insertion error model. And the third is plural feature deletion on the first noun phrase, which we call the deletion error model. So we compared 2 conditions at a time. So the first ones are A and B. Those are the sentences in which the distractor noun differs in number, and the predictions according to all 4 models are as displayed. So here in the results, we found some evidence for the insertion error and the deletion error model. There was no significant difference, which is basically what the models predicted. For conditions C and D, where C had a plural distractor noun, whereas D had a singular distractor noun, these are again ungrammatical conditions. These were the predictions, and again, we did not find any significant difference in acceptability between the 2 conditions, which supports the insertion error and deletion error model predictions. Lastly, I had predictions for 4 conditions. So we compare C and D versus E and F. So in these 4 conditions, what we found was that E and F are significantly more acceptable than C and D, which was a prediction of the deletion error model. So now our results showed support for the deletion error model, but no evidence was shown for any of the other models. Moving on to the second experiment. So here the hypothesis was that there would be unmeaningful sentences and readers might distort them to a meaningful representation using case marker interchanges or noun position interchanges. So in a sentence like school में शिक्षक को छात्र ने किताब से पढ़ाया था. So this is non-meaningful because शिक्षक को छात्र ने पढ़ाया था. Now people might distort it by making an interchange between the case markers of the first 2 nouns, which would be school में शिक्षक ने छात्र को किताब से पढ़ाया था, which would become meaningful, or it would become school में छात्र को शिक्षक ने पढ़ाया था, that would also be meaningful. So this was the experiment design. Here I had 6 conditions. The first one was the completely meaningful sentence. B, D, E and F had animacy violations because they had an inanimate noun followed by a case marker that should be with an animate noun. And the condition C was only pragmatically unsound. So here it was school में teacher को छात्र ने पढ़ाया था. That is not that acceptable. What we found was that, of course, the completely meaningful sentence was highly acceptable. Condition C, which only had pragmatic issues, was more acceptable than the other conditions, and there were no significant differences between the sentences which featured an animacy violation. But interestingly, in the case of the sentences which would require a case marker position exchange, the sentences were highly acceptable. So that sort of distortion was made more easily than in the conditions which required a noun position exchange. And this was seen across all conditions. So as I said, sentences with case marker position exchanges were more acceptable, implying that that distortion is made more easily, and noun interchanges do not happen that easily. So basically the implication of this study is that representation distortions do occur, so they must be taken into account in theories like Q-based retrieval, because the linguistic input that we see does not remain intact in the memory, and representations change description of how sentence comprehension works. Thank you.
Thank you for mentioning name. We have time for questions.
Yeah. No, in the number feature, the number feature is getting inserted or deleted, but the swapping of the number feature is not happening. In the second experiment, which is the noun position and case marker exchange error, there the case marker exchange is more likely than noun position exchange. I haven't thought in that direction, but I will make sure. But those wouldn't involve some sort of dependency completion or comprehension. Yeah. I'm sorry, I'm not able to hear you. Oh, they were. Yeah, they were like native Hindi English bilinguals. That I don't know. So we explicitly avoided making that sort of instruction. We just told them, so they were instructed in Hindi and they were told to rate the sentences based on how correct. So they were told, आपको जितना सहज लगे sentence उस हिसाब से rate. ठीक. Yeah. So I haven't done it yet, but I plan on doing the reading time analysis. So it was a self-paced reading study. So I have the reading times. Yeah.
Then you would have times for
Yeah.
in which errors occur.
Yeah. Yeah.
All right. Thank you, Varsha.
Thanks.
We'll move on to the next talk. The next talk is by Pranav. Length and modality impacts subject drop, corpus study movie. Pranav is from IIT.
Hi everyone. I am going to talk about how length and modality impact this phenomena called subject drop, and I am going to show a corpus study to test whatever hypothesis I have. So first of all, what is this phenomena of subject drop? So imagine you are talking with a friend and you do this thing where you don't always utter the subject of the sentence. You omit the subject, and that is what subject drop is. Something like you can say tum khana kha lo in Hindi, which means you eat food, but you can also say khana kha lo, which is equally okay, where you drop the subject. Now this is the phenomena of subject drop, and what I am interested in is understanding how subject drop is impacted by processing pressures. So previous studies have shown that the number of arguments of a sentence impacts subject drop, where arguments are basically subjects or objects a verb needs to be grammatically okay. So something like a verb can take one argument, where something like gorillas exist, 2 arguments, Raju opened the door, or 3 arguments, Babu Rao gave Devi Prasad a bottle. So as you can see, for example, in 2 arguments, you just cannot stop by saying Raju opened, right? Or for 3 arguments, you cannot say Babu Rao gave Devi Prasad. You need to say something else for making it correct. So these studies show that when they compared 1 argument and 2 argument sentences, they found that 2 argument sentences showed more subject drop. So why should that be the case? What they proposed is that subject drop facilitates maybe in somehow the process of sentence production, although they don't specify why or in what manner that should happen, what is the exact process, and that is what I am interested in. So let's think of some possibilities. One could be just the idea that you don't want to put that much effort and just you want to speak one word less, right? For example, in first condition, you have gorillas exist, which is smaller than the second condition. You are saying a lot of sentences. You want them to be you want to put less effort, so you drop one from the second kind of sentences. There can also be interference in memory. So you have whenever you are speaking a sentence, you need to also keep a lot of items in your memory, right, which can interfere with each other. So having one less item will help you, right? There can be other factors which are not related to facilitation per se, but more in like memory terms, but more in terms of information kind of a way, like for example information content. So in 2 you see that opened the door, right? These 2 information can help you better to know what the subject was, right, than just exist in the first case. So there can be 3 ways. So interestingly, all of this can be related to length, right? So eventually, if you want to speak one word less, you are decreasing the length. Interference, again, if you have a bigger sentence, lengthier sentence, you have more material which can there are more items which can interfere with each other, so you want to decrease that. Or again, if you have more information content with a longer sentence, so you have more idea about who the subject was, so you can easily drop it, right? So that is why I am asking this question, whether the effect that we saw from the arguments, that is because of length, right? So the first hypothesis is whether length impacts subject drop. But in the keynote, we talked about, there was something which I am going to repeat here, which is that there are several stages of production, right? You conceptualize whatever sentence you are going to say, then you formulate the entire sentence through a set of stages, then you articulate the sentence. So the idea is that this process is not serial, where you take the entire material of the sentence that you are going to say and process it at one stage, wait for it to be processed, and you move on. You instead do it more in a incremental fashion, where you just push it forward as soon as it's done, right? So this then is weird for that hypothesis, where we know that subject position is at the beginning of the sentence, right? So also the decision you need to take for whether you drop a subject or not, that also needs to happen in the beginning. So you don't exactly know the sentence length which should come at the end, right? So hence we have the second hypothesis, which says that length just cannot have any impact. But then there is this third hypothesis, because see, previous studies showed that arguments have an effect, right? So there can be this thing that we can ask this question: how much is the message level incremental? How strict is it, right? So previous studies have shown that, we have a coarse knowledge of the event before sentence formulation. More importantly, we know who did what to whom. This study, as well as recent work in the lab, which was shown in the keynote, we kind of know who did what to whom. So we know the number of arguments that are going to come, right? So hence we have at least a boundary threshold at the message conceptualization stage. So we can have the third hypothesis, which is it's partially incremental message, where length, of course, we don't know, but we want to eventually offset the effects of length. So we do this, where we take arguments and use it as a proxy, right? So we want to now test these three hypotheses and see what is the case. We want to do it through a corpus analysis, but we need to be cognizant of the fact that whatever hypothesis we made is we assume that there is a moment to moment online processing of which leads to a sentence. We produce a sentence. That is what we were thinking. So written corpus is problematic in that sense, where some of the assumptions just won't hold about incrementality, where you have this corpus might have a lot of revisions, so these things will just not play a role. So it is very important to investigate such a question in speech corpus. So previous studies have looked at both dialogue and written combined, but they did not do a comparison between the two. We are going to take Hindi, a written corpus in Hindi, which is the HDTV corpus. We are also going to take the dialogue corpus, which is the ITD dialogue corpus. And what we are going to do is we are going to look at matrix arguments. So a sentence, the arguments at the main clause. You can also have embedded sentences, but it is a bit tricky to know about the subject drop. So I am going to keep it simple and just check how many arguments are there at the matrix level, right? And we are in both of the corpora, we only took sentences which had a matrix verb, of course, and the sentences with 3 arguments were pretty less, so we just considered 1 argument and 2 argument structure, similar to previous studies. The dependent variable here was the proportion of subject drop. There were 3 independent variables. The 3 factors were number of arguments, sentence length, and then modality, whether it's written or it's dialogue. We fit a simple linear regression model, and there could be this was how it was. Now, what are the predictions? First of all, length hypothesis will say that there can be an effect of the number of arguments as well as length. A strict incrementality hypothesis will say that none of them will have an effect. On the other hand, a partial incrementality hypothesis will say that number of arguments will have an effect, but sentence length won't.   .                                                                                                            Now let's come to the results. What are the you can see here okay, sorry. The x-axis is the number of arguments and the y-axis is the rate of subject drop. So you can see that there is an increase in subject drop from going from one argument to two argument. Similarly for dialogue, we also found an increase. One thing we found different is that there is a lot of more subject drops happening in dialogue than in written, right? So we found a significant effect of number of arguments. We also found a significant effect of modality, where pro-drop is more actively done in dialogue. We found no significant difference between the effect of number of arguments for dialogue versus written. Now, what about length? So actually it looks like this. There is for the written corpus, there is a lot of rarer sentence lengths, but if we can zoom into the area which is a bit more stable. On the other hand, you can see that the Hindi dialogue corpus looks much more stable. Again, there is a more like part which is better than the rest, so we just zoom in there. Overall, we can see somewhat of a downward trend, which seems much better in dialogue than for written. We found a significant effect of length. We also found a significant effect of interaction between length and modality. So it was much more prevalent in dialogue than for the written corpus. Now what is the current scenario? So the current scenario is that we found an effect of number of arguments. We found an effect of number of the sentence length. But what is interesting is that we found opposite effects. If you look at this, there was a downward trend here, but for number of arguments, it's increasing, right? So that is important here. So once, although we found the effect from both, saying that length is the one which was what was at play for the effect that we found in number of arguments will be wrong here, right? Again, strict incrementality is of course not the case. What about partial incrementality? So how we had framed it, it seems like that's not the case, but because we did not just find it for arguments, we also found it for length. That is not the, of course that is not what we found, but it could be the case that there is some partial incremental thing happening, and that is what I think we can make sense. There is one way to make sense of the results in that way, which is that we did this thing in the beginning where we talked about uttering one word less is what is driving. So that is of course not the case because length is not there. But there can be other things which might still be active, for example, interference. So it could be the case that arguments interfere with other arguments more and other material doesn't matter much. Or information content, who did what to whom information is more important, right? The argument information is more important than others. So that could still be active. Because there is a different direction in the effect, right? We cannot like combine both of them, saying that both of them are showing the same thing. I think this is the length, the effect that we saw is something else, which is like we do subject drop when it can be inferred from context. Simply put, enough information is given there. On the other hand, if the information is less, you will do less subject drop, right? So it could just be the case that information is less, so we are like saying longer sentences, right? We don't know the length, but we are just, because of this thing, because of how much information is there given, we say either longer sentences or shorter sentences. So key takeaways are length might not be impacting right now subject drop directly. Arguments do impact, as we saw, and it could be more about given information, the effect that we saw for length. Thank you. Very different. Yes, yes, yes. That difference is of course there. That whatever process that leads to subject drop is much higher in a dialogue or spoken corpus than that, for sure.
The temporal dynamics of visual word recognition, morphological timing in a morphologically rich language.
Hello everyone. So today I'm going to be presenting some data from a visual word recognition study that we did. This was initially done as a cross-linguistic comparison between Malayalam and Bangla. I'll be presenting the Malayalam data today, and time permitting maybe show you some interesting things that are happening in the Bangla data as well. So this motivation to study visual word recognition really comes from trying to understand how it is that you are processing words in all these different kinds of languages. And a good place to start begin to start asking this question would be to think about, well, what are the ways in which these languages sort of differ, right? So when you're presented with a word, through reading, for example, what are the kind of features of the word that you have to keep track of? So there's obviously a lot of different features, but I'll talk about maybe two of them. One, of course, is the script of the word that the language is in. So Professor Hussain kind of talked about this already. So I'll direct your attention towards the scripts that languages closer to home are written in, which are abugidas, which is where words are represented as consonants, and the vowels are represented as kind of diacritics marked on the consonants. Another way to think about how they differ is in terms of word structure, or how words are formed in languages. So this is morphology. Again, I'll just maybe talk about agglutinating languages. So a lot of your Dravidian languages spoken in the south are agglutinating languages, where you might have, say, a verb like to speak, and you kind of stack or glue suffixes or morphemes very productively onto this verb to create something like I am speaking in Tamil, right? You also have fusional languages where this sort of morpheme distinction that you see in the agglutinating languages is not as clear. Morphemes are kind of getting fused together to form something like the Spanish example here. So just to give you some context, English is, if you think of this as a spectrum, for the most part, somewhere towards the isolating side, where you don't have this kind of fusion or gluing together happening as much. Hindi is also somewhere around there, but you do see fusional features happening in Hindi as well. So I'm quite interested in this aspect of word recognition. How is it that morphology might be helping you recognize a word? Or how might we be identifying morphemes when you are presented with a word? Now, I'm quite interested in how this happens in Malayalam. So I've tried really hard to translate this particular phrase in Malayalam into English and Hindi, which obviously has not happened. But the best translation I can come up with is something, in English, is something like, this phrase can be translated into English by saying something like, the song which had been in the past being taught to someone, right? Now, all of this information, I can pack it into basically 2 words in Malayalam. So this is just to kind of give you a sense of the level of morphological complexity in Malayalam and why it might be worth investigating word recognition processes in this language. And if that's not enough to further impress upon you the degree of morphological complexity, I have this cool graph that looks at one aspect of morphological complexity. This graph basically tells you, if you look at a text corpus, how many novel word forms are you going to encounter as the text corpus grows, right? So if you see the Punjabi, English, Hindi sort of curves, they plateau after 2 or 3 million, whereas Malayalam, Telugu, some of these Dravidian languages are still kind of going strong, right? Right, so the example that I showed you in the slide before, that's probably, you're not going to encounter that in regular speech between Malayalam speakers. I would probably drop a suffix or 2 or find another way to express that same thing. The kind of words that we are going to be looking at in this study is more of this type, right? So this had plus ed sort of construction, I can make in Malayalam using suffixes. One thing I want to point your attention to is, again, look at the boundaries between the morphemes. They're quite clearly identifiable, and you would assume that a Malayalam speaker would be able to extract this kind of structure pretty efficiently. Also, the sort of grapheme to sound correspondence that Professor Hussain touched upon in his keynote is also fairly consistent in a language like Malayalam and most agglutinating languages for that matter. So the assumption here is that, well, if a language is morphologically rich like this, its readers must be quite sensitive to the morphology, to the morphological structure to be able to parse them. And that too, this should happen fairly early on. When you're presented with a word, this process should start early on. So work that has looked at the influence of morphological structures typically try to dissociate effects of morphology from other sort of factors by doing priming experiments, right? So you present participants with these kind of prime target pairs like departure and depart, if you want an English example. And what is fairly consistently like attested is that the recognition of the target word depart is kind of facilitated in terms of reading times because you've just seen a word like departure, which is a morphologically related word. Why you see departure, you kind of decompose that word into maybe depart plus the suffix, and so then you see depart depending on what model you subscribe to, but there's some kind of residual activation there and you recognize this word faster. So morphological decomposition kind of happens, is something that we know for the most part. And this kind of priming effect basically suggests an access mechanism or maybe even some kind of underlying representation where that is sensitive or dedicated to the morpheme, right? But you could argue that, well, this kind of priming might actually be because of a form overlap, right? Between departure and depart, obviously there's like 6 letters that are in common, so it could just be an orthographic effect, or it could be because they're related in meaning, right? Departure is the noun form of depart, so it could be semantics actually. And so in order to tease these factors apart, we have quite a rich body of literature from the 2000s that does exactly this using the priming paradigm. So this is a fairly seminal study from the 2000s where Russell and colleagues were looking at English prime target pairs like departure and depart, which are morphologically, orthographically, and semantically related, and compared it to word pairs like electrode, elect, which are only orthographically related, and semantic controls and maybe like a baseline condition. And they do find priming effects for the morphological conditions over and above just orthography or semantics. And in terms of the time course, which is what this talk is kind of about, they find that this info, this morphological info is accessed very early on. How do they know this? They manipulate the duration for which the prime is presented, and you can kind of see, okay, at a very early prime duration, this effect kind of starts, this priming effect is seen. So in order to do this, so this is the paradigm that we implemented, this is a masked priming lexical decision. So you see the prime, you see the target. In this particular example, the prime is shown for 48 milliseconds, which we manipulate. And there's a forward mask before you see the prime. And then the participant basically has to make a decision about whether the target word that they see is an actual word or not. This is just an example, of course. This is in Malayalam, right? So in our design, the targets were always, like the depart word, they were always past tense verbs in Malayalam. The primes we manipulate on 2 dimensions. One is the prime duration, like I mentioned. So in this particular study, these are the prime durations we use. We have 5. And this is manipulated between subjects. I'm happy to talk about why we chose these prime durations, maybe towards the end of the talk, or I don't know, in case you're interested during the Q&A. But I want to focus on the other manipulation that we did, which was the type of prime, right? So what we have done is have 2 morphological conditions. So one of them is the same verb root as the target, but it also has the continuous aspect suffix. So for a target like go, you would have was going, okay? You also have another morphological prime, but this time with the perfective suffix, so had gone, something like that. And then you have an orthographic condition which just has some overlap in terms of form and an unrelated baseline. So to give you a sense of the stimuli that we used, I have English kind of analogs of the Malayalam stimuli. So this is the sort of level of overlap between condition A, the morphological continuous and the target, morphological perfective and the target, orthographic and the target. Although this example is a little misleading because the overlap was at the syllable or the graph level, whereas here it just looks like it's at the letter level. And then an unrelated condition where there's no relationship whatsoever. We had 100 participants for this experiment in Malayalam and 50 critical stimuli, which is mixed in with fillers and non-words. We also did a short SPR task beforehand to make sure that, okay, participants were actually proficient. Okay, and this was pre-registered on OSF. So this is a little bit exploratory in terms of time course. We don't really have work in Malayalam. We have a lot of work in agglutinating languages, but not with the kind of script that we're dealing with. But I think it would be safe to assume that, okay, you're going to see morphological effects pretty early on, and for us to say a morphological effect is happening, we would have to see reading times in the morphological conditions being significantly less than the unrelated one. As far as the orthographic condition is concerned, we've seen like all kinds of evidence for orthographic effects in the past. We've seen facilitatory effects happening early, inhibitory effects happening late. So you see something like electrode and elect, and you're going to delay your recognition, basically. So it could also be the case that we find inhibitory effects later. And in the 2 morphological conditions, like I said, in Malayalam, these suffixes differ in terms of frequency, right? So these are basically raw counts. So you're going to maybe see an effect of this also in this experiment. So we fit linear mixed effects models. So the central predictor, the main predictor is obviously prime type, but we also have control variables like I just said, the prime suffix frequency, but also the target's whole word frequency, and something to account for the script complexity of the language, which is similar to the orthographic complexity metric that Professor Hussain talked about, and also a kind of proxy of word length, which we're going to call syllable length, but I've just written word length so as to not confuse you. And this is the distribution of mean RTs across prime durations. So just to walk you through what we're seeing, at very early prime durations, 48 milliseconds, we're seeing an effect of the morphological continuous condition, right? Nothing, yeah. And then at 450 and 600, much later, we're seeing effects of both morphological continuous and perfective conditions relative to the unrelated condition. The only sort of hint of an orthographic effect across all prime durations is at the 150 millisecond mark, where we see an inhibitory effect. So this is not facilitatory. And these are the numbers in case you're interested. And apart from that, you know, just to, we also found effects of target whole word frequency at all prime durations and prime suffix frequency over and above the effect of prime type at these 2 particular durations. How much time do I have? 3 minutes, okay. I'll quickly try and run through the Bangla data. So Bangla is a little different in terms of its morphology, typology. It's not agglutinating, it's fusional, like the Spanish example we saw before. So as you can see here, the kind of morpheme boundaries are not as easily distinguishable. What is interesting about Bangla is that the script is also relatively more opaque. So a word like lotus in Malayalam would be pronounced tamara and would be written as ta plus ma plus ra in the script. Whereas in Bangla, it would just be written as the sort of consonants k, m, l, but it's pronounced as komol, like you have to infer it from the context essentially. So the orthography is a little more opaque, whereas it's a lot more transparent in Malayalam. And this comparison we thought would be interesting to see. I just want to show you the time course effects in Bangla as well. We actually found effects for both morphological conditions at all 5 prime durations in Bangla, no hint of a orthographic effect, and an effect of word length that maybe I won't go into. But we also wanted to see the extent of priming between these two languages, right? We thought that because Bangla is slightly more opaque and the kind of morpheme distinction isn't as easily distinguishable, it could be the case that maybe they get a better priming advantage than Malayalam speakers, or it could be the other way around where Malayalam speakers are so used to this kind of passing routine, they see this on a regular basis, so the morphological priming effect would in fact be stronger for Malayalam speakers. So those were our 2 rough hypotheses that I don't have time to go into now, but what we find is that the priming effect for the continuous morphological condition at the earliest prime duration was actually a lot more in Bangla than Malayalams, meaning that Bangla speakers were getting a little bit more of a priming advantage, which we speculate is because of the kind of script and the morphemes that they're used to. We did not find this effect at later prime durations. So to conclude, in Malayalam, we're seeing, well, some sensitivity to morphological structure happening at earlier prime durations and then kind of more robustly at later durations. The only effect of orthography that we saw was inhibitory. And apart from this, in Bangla, we saw that morphological effects kind of emerge at earlier durations and then sort of persist throughout the longer ones. And we also saw some evidence, some very quick evidence to suggest that Bangla speakers seem to benefit more from the morphological primes than Malayalam speakers at shorter prime durations. These are some of the references that I've used in this talk, and thank you. What prime durations are? I can't hear you very well, that's the problem.
He's asking about the role of prime durations. I'm asking that what prime durations are doing in the lexical languages for them to get activated depending on different exposure durations of the primes.
What prime durations are doing?
For the lexical activation. Mechanistically. So how the threshold activation is reached?
Oh, the threshold activation doesn't differ based on the prime durations. We're positing the same sort of access mechanism threshold activation for all prime durations. The prime duration is just, you see the prime for this long. But we don't, we're not saying that a different mechanism is in place for different prime durations. So the classic sort of explanation is in terms of, depends on which model again you subscribe to, but if you're doing lexical access and you see something like departure and you see something like depart and you decompose departure, depart and URE, and then you look up the lemma in your sort of mental lexicon and then you access it, right? And what orthographic primes must be doing is you are misled into believing that there is some overlap. So you start maybe, you even though electrode isn't sort of, it's like a pseudo whatever word, right, which you can decompose into elect and road or whatever. This is a hypothesis that's been posited by, say, for example, Russell and colleagues, who describe the orthographic inhibitory effect using this explanation.
So I see graphemic complexity also used. How do you estimate graphemic complexity
Yeah.
for Malayalam, right, which is linear, everything comes.
So I have some appendix slides. So I've used the Hindi example here because I thought this would be more whatever, but this metric for Hindi was developed in Hussain et al. 2015, where you penalize basically any kind of asymmetry in or mismatch in the way something is spoken and the way something is read. So the Iki Matra, for example, that Professor Sen talked about in his keynote, where you would probably, it should be read as iblu, but you don't, you say bli, right? So those kind of things are penalized. So the Malayalam one was taken from the school study by Shalom and Vaidya. Malayalam has some idiosyncratic sort of these kind of features on its own. So these things are also penalized in our metric. So the Bangla graphy में complexity stuff was adapted from the Hindi, this Hindi metric, and the Malayalam was taken from this particular paper.
Sorry, I'm slightly under the weather today. Hello, my name is Sandeep Kaur, and today I'll be presenting my study titled Age and Structural Differences in Multilinguals, Effects on Attention and Inhibition. So, to start with, multilingualism is a very complex phenomenon that goes far beyond simply knowing two or more than two languages. While this basic definition is technically correct, multilingual experience actually involves multiple important dimensions that involves, influence how individuals learn, use, and manage their languages. Because of this complexity, multilingualism cannot be fully understood by just counting the number of languages someone speaks. Earlier research mainly focused on comparing multilingualism or bilingualism versus monolingualism, and especially in terms of executive functioning. Some influential research by Bialstock and Costa, they also reported that bilinguals demonstrated certain cognitive advantages over monolinguals. However, many other studies have found no such differences, leading to mixed conclusion in this field. So a big question is, why were the findings so inconsistent? One major reason could be that multilingualism was treated as a categorical condition, as if all multilinguals, they follow a homogeneous group. But what about the important experiential dimensions of being a multilingual? Although more recent research has focused on the nature and the quality of multilingual experience. So instead of only asking how many languages someone speaks, now studies are looking at important factors such as the context in which the languages are used, the age at which the second language or the other languages has been acquired, the frequency of language use, proficiency level, the structural similarities and differences. So overall, the idea that multilinguals naturally outperform monolinguals is not that straightforward. Cognitive differences, if they appear, they likely emerge from when the second language is acquired, how it is used, what is its structure, what is the proficiency of a speaker, rather than just being a multilingual in a categorical sense. To move beyond the idea of multilingualism as a category, we now look at what previous studies have found about specific factors that actually influence executive control. So a growing body of evidence indicates that the age at which languages are acquired, I mean the second language or the other languages are acquired, it plays a very crucial role in shaping the executive control. For instance, Capa and Colombo, they found faster reaction times among early bilinguals. Cosi, she also reported better interference suppression and more efficient brain networks in simultaneous bilinguals. Yo and Lee, they also observed that early acquisition was linked to smaller interference effects and improved conflict resolution. So together, these findings, they suggest that early acquisition of multiple languages might provide us cognitive benefits. So another important experiential factor that needs to be considered is typological difference. Research in this area is also, it has also quite mixed findings. While some studies report that a greater language similarity enhances executive control, others suggest that managing typological distant languages strengthens cognitive mechanism. So this also raises a very important issue that how the typological differences are being defined and measured also influences our research outcomes. So a more precise approach involves examining specific linguistic dimensions which would help clarify how particular structural feature and which feature in particular interact with other multilingual experience to shape cognitive performance. So our present study, it examined two important experiential dimensions of being a multilingual. First is age of acquisition, and the second is typological differences. We particularly we have taken word order in this context and how they interact to influence inhibitory control and attention. So we specifically looked whether the multilinguals, they acquired their languages simultaneously or sequentially, and whether the languages they spoken, they follow the same word order or different word orders. So based on previous evidence suggesting that early acquisition of multiple languages might give us cognitive benefit, we hypothesized that simultaneous multilinguals would perform better in inhibitory control task and attention than sequential multilinguals. When it comes to typological differences, the findings were quite mixed, so we did not predict a specific direction of effect. Rather, we hypothesized that multilingual speaking languages with different word order would differ in inhibitory performance and attention from those who speak languages with same word order. And we also tried to examine the combined influence of age of acquisition and word order differences on inhibition and attention. So we hypothesized that the impact of simultaneous versus sequential acquisition may vary depending on the word order similarity of the languages spoken. So we used 2x2 between subject randomized experimental design. A total of 99 participants were taken, 47 of them were males and 52 were females. They voluntarily took part in the study, and all were either graduate or postgraduate students and self-rated proficiency in all their languages. And participants were divided into 4 groups based on age of acquisition and word order. So this is how they were grouped. So first group was simultaneous multilinguals with same word order, in which it contained participants who were exposed to 2 or more languages simultaneous before the age of 3, and with all their languages sharing the same word order. For example, Hindi and Punjabi, they both dominantly shared SOV. And simultaneous multilinguals with different word order contain participants who learn 2 or more languages simultaneously with different word order. Sequential multilinguals with same order contain participants who learned an additional language or other languages after the age of 3, where all the languages shared the same word order. Similarly, sequential multilinguals with different word order contain participants exposed to second language or other languages after the age of 3, where the languages differ in word order. So this is how we used 2x2 factorial design to group our participants. Okay. So to assess participants' cognitive inhibition, or rather prepotent inhibition, we used the Stroop color and word test by Golden. It was a pen and paper version, and it contained 3 pages. The first page is known as word page, where participants, they read aloud color names printed in printed in black ink. It was quite simple, right? And then the second page is known as color page, where participants name the ink color of series of strings. So in the second page, they named, blue, red, blue, green. And the third page is known as color and word page. It is an incongruent condition where participant named the ink color of incongruent color word. So here, what would be our automatic response? It would be to read the word red, but instead the participants were supposed to read the color of the ink, which is blue, instead of the word. So this is how we done this. So each page was timed for 45 seconds and the participants were instructed to complete as many items as possible. Then raw scores were taken and then converted into T-scores using age and education predicted scores table by Golden. And higher T-scores, they indicated better inhibitory control. The attention task was designed using Open Sesame, although it is not a standardized paradigm for assessing the attention. So this is, okay. So the participant saw the stimulus for 180 milliseconds, followed by an interval of 500 milliseconds, and then 4 orthographically similar words would appear, and the participants were supposed to choose the correct word. So 20 trials were conducted and attention was measured through reaction timing and accuracy. Okay. So coming towards results, we first ran two-way MANOVA to examine the effect of age of acquisition and word order on inhibition and attention. We found significant main effects for both the factors as well as, influence of the, so as well as significant interaction effects. So to rule out the influence of number of languages, we did not control for the number of languages. So to rule out that possibility that it could have a confounding effect, we conducted separate ANCOVAs controlling for this variable, and overall the result patterns were similar. For inhibition, significant main effects of age of acquisition and word order were observed along with significant interaction effects, but for attention, only the main effect of word order was significant. So overall, the simultaneous multilinguals performed better than sequential multilinguals, especially the effect was more profound when their languages had different word order. So, so the findings, they confirm that age of acquisition influences our cognitive performance. We think that this advantage may stem from their continuous management of multiple linguistic systems, which requires frequent inhibition of non-target language. So over time, this repeated need to inhibit competing linguistic system, they may naturally strengthen their inhibitory control. Participants with different word order also showed better inhibitory control, which highlights the role of syntactic diversity in enhancing executive functioning. So importantly, we observed that simultaneous multilinguals who were exposed to different word order, they showed the highest inhibitory performance, whereas sequential multilinguals, they showed minimal differences across word order condition. This pattern actually makes sense because simultaneous people, they acquire their language before the age of 3, and they spent longer time juggling among different syntactic systems. So they repeatedly practice selecting target structure and suppressing the non-target one, therefore maybe enhancing their cognitive performance. So for the future direction, first of all, I would like to acknowledge that this study is not without its limitation. But for the future, I would like to extend this study by including more experiential factors such as proficiency, frequency of language use, and age of acquisition, typological differences to better understand how they impact our cognitive performance. And also, I would also love to look into other dimensions of typological differences because in this study, we have just taken word order. And and another important direction would be to, other direction would be to include more uniform and well-defined participants with linguistic background. So with this, I conclude my study. Thank you so much for listening to me. Thank you. Yeah. Yes, actually, this could be a limitation of our study because we did not Actually, at that time, our main focus was to recruit participants with the participants from the linguistic backgrounds who had, they were deferred in terms of age of acquisition and, word order. So we actually like asked them. So we did not actually control for the proficiency. Yeah. And actually, even the variability of languages. So that is why I really want to extend the study by including more uniform population. Yeah.
Any more questions? If not, then thank you, Cindy.
Thank you so much.
So that brings us to the end of this session.
Good afternoon, everyone. I am Manvi Joya from IIT Gandhinagar, and today I am going to talk about mechanisms underlying savings in visuomotor adaptation. So first, let's understand what is motor adaptation. Motor adaptation is a process by which individuals adjust to their movements to compensate for the environmental perturbations to ensure the accurate motor performance. And these perturbations, they kind of induce errors, and errors in experimental setting we can induce by variety of ways using prism glasses, visuomotor rotations and gains, force fields, and etc. So primarily, at least there are two learning mechanisms that play a role in sensory motor adaptation, which is the fast process and the slow process. So this fast process acts to rapidly reduce the errors, whereas the slow process causes gradual refinements to your motor plans. And the fast process is thought to reflect deliberate explicit strategy use, whereas the slow process is believed to drive implicit updates to this internal motor model. And there are two types of error that is linked to these processes. First is sensory prediction error, and the other one is task performance error. So this sensory prediction error is basically discrepancy between what is your actual hand movement and what you expected, and this drives the implicit mechanism, whereas the task performance error is basically when a participant is unable to reach or perform the task goal perfectly, and this drives the explicit strategy use. So let's understand what is savings. Savings is a phenomena in motor adaptation which refers to the faster relearning when the participants are exposed to the same type of error or perturbation the second time. And the mechanisms that give rise to savings is very unclear. So one view talks how the explicit strategies could give rise to savings, whereas the another talk how the slower mechanisms also contribute. So in one of the study by Sedafel et al., point targets shifted to 45-degree counterclockwise once the participant initiate the movement. So they were instructed to reach to this new target, and which was the so in the graph on the y-axis you can see that there is hand deviation, and on the x-axis that is learning trial number. So this hand deviation is basically how a person deviate from, how much the person deviate from their the target. So the blue data points represents the learning block, during which we can observe that they gradually adapt to this perturbation and reaches their hand angle to 40 degree. Whereas when the same perturbation is given to them again, the pink data points you can see, so they adapt quicker and takes very few trials to adapt to this perturbation, which is 40 to 45 degree angle. So because of the shift of this the shift of the target, there is a task performance error and not sensor prediction error. So when learning is driven by TPEs only, savings is evident. But another study by Leo et al., where in which the mid movement the target is aligned with the rotated cursor to the 30 degree counterclockwise. So the participant make the movement, and in the mid movement the target jumps to the cursor. So the target always falls on the cursor, which means there is no task performance error here, but a sensor prediction error, because where you move your hand and your actual outcome is, there is a discrepancy between that. So when the same task was given to them again, they could not see any savings, which means the absence of TPEs, but in the presence of SPE, they did not see any savings. But in this, the test was on the same implicit adaptation task, and in one study by Abraham et al., the lower graph, they explained how testing presence of savings on the same implicit driven task could show attenuation. So the upper graph is by Yin and Wei. In this study, what they used was error clamp, and basically, so here they used error clamp. A clamp is when your cursor is rotated to a fixed angle. So no matter where you reach, your cursor is going to go to a fixed angle relative to your target. And they checked savings on a different paradigm, which was the rotation task here, and because of only presence of SPEs here, savings was observed. So until now we have different views how TPEs give rise to savings, and how in Leo et al. They talk about how SPE would not give rise to saving, but changing a paradigm and only giving SPEs, only checking for SPEs could give rise to savings. So we wanted to make a robust design and resolve this issue and answer the question, is savings only present when task errors are present during the adaptation, or SPE exposed during the learning give rise to savings? So our experimental setup was such that a participant is provided with a stylus and they have to move their hand on a digitizing tablet, and there is a mirror which occludes their vision to their hand movement, and they would see stimuli on this mirror. And in group 1, we used target arc as a manipulation for task success. Basically, people are instructed that you can reach anywhere in this arc, but there's a cursor feedback of 45-degree rotation, counterclockwise. So if they are reaching to 90-degree angle, they will see their cursor to 45-degree rotation. But so here there is no task performance error, because their task is basically to hit this arc, but a sensor prediction error because of this cursor rotation. So in the group 2, there's a point rotation task, which is they have to reach to the target, but they are instructed that your cursor should fall on the target. So if they are reaching to 90-degree target, they would see their cursor 45-degree counterclockwise rotation. So they would have to move to 45-degree in order to hit that 90-degree target. And we have 5 different locations of target: 360, 135, 90, 45 and 180. So here there is a task performance error as well as sensory prediction error. And also to check if people are adapting implicitly during the ARC training group, we have these catch trials embedded during the learning and the washout. So in the catch trial, so a catch trial is basically a 90-degree target that you would see on your screen, and you would have to reach to the target, but there will be no feedback in this. So these there were 30 catch trials in the learning and the washout period. So my experimental design is such that there are baseline point target followed by the arc target, and this is basically the learning block, the second block, and they have the catch trials with no feedback, but a cursor feedback rotated during the arc trials, and then there's a washout which is done again on the same arc only, and the catch trials are also embedded in it. And then are the savings block, basically the test block, which is the point target. Here again there is a 45-degree counterclockwise rotation, and similarly in the second group, it is the point training group. In the place of arc target, we have the point targets only with the catch trials, no feedback, and the washout with having veridical feedback and catch trials, no feedback at 90 degree. And then again the test block, which is same across the groups. And then third one is the control group, the naive group, which is they are trained on the long baseline point targets with the veridical feedback and the test block. So we are going to compare the arc to that of the naive, and the test block of the point training to that of the naive group. So our results were such that in the point training group, you can see we have hand angle on the y-axis and bins on the x-axis. So I have taken 5 trials in one bin, and then we have averaged that out, and I have 16 participants in all the groups. So we can see that people show gradual increase in the hand angle during the learning block, and then they come to the baseline in the washout period, and then they again show faster or quicker adaptation to this perturbation in the test block, which is the last block. And in the third naive learning, we can see that in the test block, they are gradually adapting to the perturbation that was given to them, which was 45-degree counterclockwise point rotation. So the catch trials comparison to see how much implicitly people are learning during the arc training. So we can see that sorry. How do I use this? Sorry. So the blue represents the arc training and the red represents the point training. So we can see that the arc training group is also kind of adapting to the perturbation, even though they are told to reach anywhere in the arc. But because of the catch trials and no feedback, we can see the blue line, it goes to 0 degree to 20 degrees approx, and the red line, which is the point training group, they kind of adapt to it from 20 to 45 degree, and then coming to the baseline in the washout. And we've also done the difference. We've taken the mean hand angle on the bar plots that you can see. The upper one is for the learning block, which is very significantly different, and the down one is for the washout, which is the similar. So for evaluating savings across naive and the R group, we have taken only the 5 bins, which are the 25 first trials in the test block, and we then also did the upper graph that you can see is the mean hand angle, and we did permutation testing to find out the statistical effect that we see is not by chance. And here the p-value is 0.23, which is basically savings is not observed in the R training group compared to the naive. So just SPE during the learning is not sufficient for savings. Then we checked the savings across the point training group and the naive group, and we could see a clear difference with the p-value of 0.0007, and savings is observed in the point training group compared to the naive. So which means when there is presence of task performance error, you could see savings. Then also what we did was we compared the test block of the ARC training group to that of the learning block of the point training group, which was basically we wanted to see how they are behaving, because in the ARC group they had ARC target in the learning, whereas in the point group they had this points target which the ARC group was which the ARC group observed during the test block. So we found, again we took the first 5 bins and there was no significant difference, which means that even though the ARC group, they had this sensory prediction error, the same 45-degree counterclockwise rotation, they were behaving in the same way as if they were given this perturbation for the first time. So the conclusion is basically group that learns in the absence of task performance error and presence of sensory prediction error shows similar learning to the naive group when they are exposed to the visual motor rotation, and group that learns in the presence of task performance and sensory prediction learns faster on the second exposure relative to the naive. So results suggest that a fast explicit system driven by task performance error are critical for emergence of savings. Thank you.
Hi. Thanks. I didn't get the explicit implicit part. There is no explicit measure of explicit or implicit in your study, right?
No. So actually, the errors, these drives the mechanisms.
Sure, but the question is, how do you conclude some system is explicit or implicit? There is no test of it in your own study, right?
No, so that is already there. Like, there are these two mechanisms. Basically, when you...
No, sensory prediction error can be explicit, right?
No. So it is...
In general, there is no theoretical, in principle, ban on sensory prediction error being implicit all the time. It can be, I have no problem, but...
No, so for sensory prediction error, actually, your brain, it adapts to it automatically.
That's the question. How would you say that? Because a lot of times in delayed task, I have sensory prediction error and I can report on it. I am aware of it, and it can drive, go to a restaurant, you expect it to be nice, it tastes bad, you won't go again. Everything is explicit there. Stupid example, but it's a sensory prediction error, right? So the question here is that, I mean, I have no issues with the results, that there are differences in training and results.
Any other questions? Okay, let's move on to the next speaker. So the next talk is by Navya Bajpai from IIIT Hyderabad.
दो है ना दूसरा वाला चेक करो नहीं not this 50 है क्या नहीं एक और भेजिए मेल करेंगे आप मेल खुलेगा कैसे
इसमें
मोटर मेमोरी सो इसी से डायरेक्ट से खोल देते हैं। हाँ इसी से खोल दो।
Okay. So Navya, you have 15 minutes.
Yeah. Hello everybody, sorry for the delay. I am Navya Bajpai. I am from Brain Cognition and Computational Lab, IIT Hyderabad. I'm working on temporal dynamics of sequence learning, and today I'll be talking about how response stimulus interval shapes chunking and implicit-explicit transition. So to give a brief idea, motor sequence learning is basically us trying to extract patterns from the environment. It is fundamental for skill acquisition, be it typing, music, sports. It involves coordination between planning, selection, and execution. And one of the most prevalent paradigms that are used to study motor sequence learning is serial reaction time task. I'll get to this later because this is what we have also used in our design. But first, I want to talk about implicit and explicit processing. When we talk about learning, there are two types of processing that take place in the brain. Implicit processing is mostly automatic. Suppose I ask you to type your name on the keyboard. You probably will not need to look at the keyboard. You're so habituated to it that it comes automatically. It becomes attention independent. But when we talk about explicit processing, it is more goal-oriented. Say I ask you to learn choreography to a dance. You will require attention for that kind of learning. So there have been a lot of debate, a lot of theories that said that implicit processing and explicit processing have different pathways in the brain. But a paper of 2016 from our lab said that implicit and explicit processing is actually a spectrum. All learning starts from implicit, and depending on the attention that we give to the stimulus, the learning lies somewhere in this spectrum. So whether a learning is implicit or explicit, it is modulated by attention and awareness. Now, when we talk about modulating attention and awareness, there are several factors that do that, but we focus on the temporal factors. We talk about RSI. Now, RSI means response stimulus interval, the time between responding to a stimulus and the next stimulus appearing. To give you a better understanding of it, I will first move on to the serial reaction time task. This is the task that we have also used in our study. In this task, 4 circles are presented to the participant on the screen. And in these 4 empty circles, in one of these circles, a target circle appears. And the participant is asked to press the key corresponding to the location of the target circle. Now these circles go on in a sequence. In any one of these sequences, we fix the sequence and we try to train the participant in that sequence, although the participant is not aware that there's an underlying sequence that is going on. So when a participant presses the key to a certain stimulus and the next stimulus appearing, the time interval is known as RSI. Now, for the past 25 years and more, a lot of studies have been done on RSI, where they have concluded that in shorter RSI, the shorter RSI favors a more automatic approach. It favors more procedural control. While the longer RSI, because the participant gets enough time to sit with the stimulus, almost around 1000 milliseconds, it encourages more explicit processing, more better knowledge of the sequence. But the motivation of a study was that previous studies have had advanced knowledge about behavioral and neural mechanisms of both implicit and explicit processings, but separately. No efforts were done to understand this route, this spectrum, and this switch that happens when implicit learning finally becomes explicit. So the main aim of this study was to understand the neurocognitive mechanisms that are involved when we talk about this transition, when we talk about this switch during sequence learning. So the main objective of our study was to determine whether the size of the response stimulus interval influenced sequence knowledge to become explicit in SRT task. We hypothesized that longer RSIs will allow attentional processes to kick in, which will further allow the participant to pay more attention to the elements of the sequence. And when there's more attention, there'll be better learning as the RSI becomes longer. This was the basic idea. So this was our task design. We trained the participants for 14 blocks. In each block, the participants were trained in any one of these sequences. That was known as the training sequence. And they were trained for 14 blocks, where each block had 8 repetitions of this sequence of 12. So each block had 96 trials the participant had to go through. And the 12th block, we took it as a test block. In this 12th block, we randomly introduced another sequence. To assess learning, I will get to the results later. We divided the participants into 2 groups, 250 millisecond short RSI group and 1000 millisecond long RSI group. One more interesting thing was, for every block, we started the block with a random trial so that we reduce the predictability of the sequence. There were 51 participants in our study, 25 in the short RSI, 26 in the long RSI. They were trained for 14 blocks. The block 12 was a test block. The participants were asked to respond as quickly and as accurately as possible, and they were not told about the underlying repeating sequence. We also conducted a free generation task after the training was over. That was done to check how much they can recall of the sequence. So this graph shows the reaction time performance of the participants from block 1 to block 14. We clearly see that learning has occurred in both of these graphs, both of these conditions, because there's a drastic decrease in the reaction times of the participants. We see a significant hike at the 12th block. This was where we introduced a new sequence. This was done to check whether there was sequence-specific learning or whether it was just familiarity or motor adjustment. So this significant hike shows us that there was actually sequence-specific learning that was happening. We also found that there was significant main effect of block that indicated that there was general improvement over time as the blocks went ahead. There was also an interaction that we found between block and RSI that was significant, that suggested that both of these groups, they followed different learning trajectories. So moving ahead, what we did, we calculated the slope of these two conditions, and what we found was that the 100 millisecond group exhibited faster overall reaction times and a steeper learning curve, showing that they were supporting a faster RT reduction rate, a better rate of learning, and our free generation task scores were also in congruence with what we found. They also showed that the 1000 millisecond group showed better recall of this and knowledge of the sequence. Now that we know that longer RSI group had better recall, we wanted to probe what was the underlying factor that was causing it. So we went with the behavioral marker for efficiency, chunking. Whenever we have a sequence of numbers to learn, our first idea is to break down those numbers into chunks and then learn it. These motor chunks, they improve efficiency, they reflect sequence structuring, and later when you are familiarized with them, they improve automatization. We wanted to study whether we can find any differences in the chunking behavior of the participants in the early and the late phases of training that might signal towards implicit to explicit transition. So we did a bit of chunk analysis here, where we tried finding chunk boundaries. We tried finding how a participant was chunking the 12-item sequence. So what we did, we divided the training into 2 phases. The learning phases were early and late. In the early phases, we took blocks 1 to 4. In the late phases, we took block 8 to 11. We avoided the blocks after the test sequence to maintain purity in the results. And what we did for both of these phases, we calculated the average reaction time for all the trials. And when we plotted them, we found a graph like this. This is a sample graph for you. So now our main task was to identify chunk boundaries. We followed a rule-based approach here. We said that the trial where the reaction time is higher than the phase average, significantly higher than the phase average, will be considered as a boundary. So if we look at the early phase, this is our first boundary, this is our second boundary, and this is our third boundary. So to say, we say that the participant was chunking from 1 to 5, then 6 to 8, and then 9 to 12. This was the basic idea. The chunk have to have at least 2 trials. These 2 participants are representative of the 2 groups that we took. So in the short RSI, we see that from early to late, the number of chunks, they remain almost unchanged. But the average chunk length increases. This shows that there is some internal refinement that is going on, but there is still implicit procedural consolidation that is happening. Although in the longer RSI, we do see that moving from early to late, not only did the number of chunks decrease significantly, the average chunk length also increased significantly, hinting that it is a very comprehensive reorganization was happening in the longer RSI group that showed that the participants were capable of integrating smaller chunks into larger chunks. When we took this analysis to a group level, we analyzed the participants individually. We found congruent results. In the short RSI condition, the average chunk length significantly increases from early to late phase, but the total number of chunks remain unchanged. In the longer RSI, significant increase in average chunk length is seen, and there's a significant decrease in the number of chunks from early to late phases, showing that longer RSI facilitate a more comprehensive reorganization, probably because the participants have lean more towards explicit processing than implicit. So this, I would like to conclude by saying that we did what we wanted to see. Both RSIs, they enabled learning, but the longer RSIs, they showed better retention of the, better reaction time performances, better retention of the sequence, better sequence knowledge, as I would like to say. The temporal affordances did guide the implicit-explicit progression as learning moved forward. And this was facilitated, this was sort of confirmed by our chunk reorganization analysis as well, that when we look at the difference from shorter RSI to long RSI group, we see that long RSI participants show more awareness of the sequence, there is more emergence of awareness. So now what we want to do, we want to take this work forward to neuroimaging, and we want to understand the underlying mechanism that is involved in this transition, especially in that switch that occurs from implicit to explicit. We also want to examine the individual differences that lie in awareness in both of these groups. And since this study is adaptable to variable RSIs in learning contexts, we would like to see that as well. Thank you. I'm open to questions.
So let me ask the same question again. I think you can. So yeah, I mean, I buy the chunking results and the RSI results, but why I should buy the implicit-explicit distinction? I still don't get it. I'm still not sure.
The only way I think you can tell whether learning has become explicit is when you know the participant has enough knowledge about the sequence.
Sure. So at the end of it, you do get a difference in knowledge. I agree.
Yeah.
But that just means you have more knowledge in RSI 1000 condition. But that makes sense, right? In any number of tasks, if you increase the response to stimulus interval, performance gets better. So that's a well-known finding in cogpsych in many number of paradigms. So automatically that does not mean that it is explicit. It's a relative performance difference, right?
Yeah.
It's not 0, 100 or anything.
Correct. So that is why according to what I have read, knowledge is not just implicit or explicit. We work, these both are very
You were the one
interactive
using the
systems.
implicit-explicit distinction.
No. I feel these are two very interactive systems. So that is why I say that longer RSIs have better or more explicit processing as compared to short RSI group. I don't say that it's...
Said it went from implicit to explicit.
Yeah.
All you have shown is that with RSI being longer, with more time, the chunk lengths increase, right? That's fine. I get that. But I still, that just because chunk lengths increase doesn't mean it has become explicit. One possibility could have been, you could run another study, stop at the 6th block and ask them for again explicit knowledge. If until 6th block both are implicit, then the explicit knowledge should be exactly the same or actually pretty much close to 0, right? So there are ways to probably test it out.
Yes, sir.
Maybe.
Thank you, sir. I will look into that.
Any more questions? So, favorite topic of motor learning. Yes. All right. The primary assumption that longer RSI can actually be questioned. In fact, when you are at a shorter RSI, you would be not able to process. But in a longer RSI, what happens is you could simply have a stimulus response. In fact, when we did that earlier, we found that half of the participants don't show learning at all. Just because you've got time, you are not having that motor movement smoothness when the RSI increases. This is just food for thought. We'll have it offline.
Yes.
But the entire assumption can be questioned. Any other questions? All right, so let's thank the speaker and we move to the next. And the final talk of the session by Naman Payasi from IIT Delhi.
This one, no? Not this one. Not this one. This is the PDF. I sent an updated one. Not this one. Yesterday I met someone and informed them, they said, oh yeah. Yeah, this latest one. Yeah. Hello. Okay. Sorry for the delay. So, good afternoon, everyone. I'm Naman, and today I'm going to talk about our project where we tested whether eye tracking can be used to detect the mental states of mind wandering and mind blanking. So, what is mind wandering? So, imagine a person reading a book. Now, it is possible that the person is actually focused on the book and has thoughts about the book. We call this the on-task state. And it is also possible that the person is actually looking at the book, but the thoughts are not related to the task. Maybe he's planning about his vacation or he's thinking about what to have for dinner. And that state where you're perceptually decoupled from the external task and the thoughts are not related to the task, we call it mind wandering. And research shows that about 30 to 50% of our waking hours is spent mind wandering. So statistically, some of us here might be mind wandering. So yeah, we should shift from mind wandering to on task, at least for the next few minutes. So how does mind wandering affect behavior? So it has been well established in research that mind wandering increases reaction time, stopping latency, decreases accuracy, and reading comprehension. But you might ask the question that why should we bother classifying mental states? You know, at best, you might not remember what you read, right? But when we see it in different scenarios, in a different context, so research shows that mind wandering is associated with poorer driving. And you take a step ahead, and when you look at high risk and high vigilance scenarios, such as imagine truck driving or air traffic control, and there, just little lapses of attention can cause really serious accident. So one of the possible application is that if we can prove in principle that the mental state classification is possible based on eye tracking, then it can be applied in a lot of safety scenarios, such as real-time detection of mind wandering, so that we can alert personnel and prevent accidents. And why eye tracking? So you can just imagine a truck driver with EEG electrodes. That doesn't seem very practical. So that is why we chose eye tracking for this. So classifying mind wandering is not new. A lot of work has already been done previously where people have tried to classify mind wandering and on task, and they have reached about 60% classification accuracy. But there were several limitations in their studies. First, there were only two mental states. So there was on task and off task. Off task includes mind wandering. But recent research has suggested a new mental state called mind blanking. So in on task, your thoughts are related to the task. In mind wandering, you are perceptually decoupled and your thoughts are not related to the task. In mind blanking, you just have no thoughts. The characteristic feature of mind blanking is an empty mind. So, and there have been suggestions about different behavioral as well as neural markers for mind blanking. So we included these three mental states in our model. So on task, mind wandering, and mind blanking. Secondly, since we were trying to create a generalizable classification of eye metrics, so generally people use only reading task for this classification purpose. But we actually chose two different tasks which are very common in mind wandering literature, such as go, no go and the reading task. So for the reading task, we took a chapter from Bill Bryson's short history of everything, where a trial looked like this. So there would be a sentence, you press a button, and then you move on to the next sentence. For the go, no go task, if you see a circle, press a button, and 30% of trials would be a square, where you have to withhold your response and not press a button. So these were the two tasks that we used. So we got 16 participants, and we asked them to do reading and the go, no go task while we recorded their eye movements. And then after every 30 seconds, so how do we know what mental state they were in? So after every 30 seconds, this appeared on their screen. So this is a probe, a mental state probe. So we would ask them in the previous trial, where was your mind? So if they say 1, let's focus on the task, we would say they were in on-task state. And that is how we got the information about the mental state of the participant. And in the mind-wandering literature, it is common to assume that the prior 15 seconds from this response, we can assume that the person was in that mental state. So for the go, no go task, imagine if the trial sequence was like that. And at the last go trial, after the last go trial, the probe appears. So and if the person says 1, then we can group the prior 10 trials as well of on task. So we did this trial grouping, and we got trials for the on task, mind wandering and mind blanking. And then we compared behavioral and eye metrics across on task, mind wandering and mind blanking, and we also attempted to model. So what are the two main objectives here is first to show some evidence that these mental states are indeed different, and this would support treating them as separate mental states in our model. And second is asking whether we can actually classify them, and are the features task general or task dependent. So let us move on to the first question. So we looked at some behavioral metrics. For the reading task, we looked at mean reading duration, so the time taken to read a sentence. And we saw that a significant difference between mind wandering and on task, where we saw that mind wandering had the longest reading duration, which means there is reduced engagement from the external task. For the go-no-go task, we were not able to find any significant pairwise difference, but interestingly, we saw significant no-go trial error. So what is a no-go error? So originally, if you see a square, you were supposed to do nothing. But if you see a square and you press a button, that is called a no-go error. And we saw that the errors were highest in mind blanking, followed by mind wandering, and the least in on task. Since there was no significant difference in the reaction time, so this is not because of speed accuracy trade-off, but because of a general disengagement from the task. Hence, these behavioral measures give some evidence that these mental states are actually distinct. Moving on, we looked at some eye metrics as well. I'm going to present 3 results. The first is pupil size. So pupil is the black opening at the center of our eye, and the size of the pupil controls the amount of light that enters our retina. So if the pupil size is larger, more light enters. So if you are focused externally, pupil size increases, and more light, more information enters. So we would expect that for on-task state, the pupil size should be larger, whereas if you are distracted or you are not focused on the external task, the pupil size should be smaller. And this is what we see. So for mind wandering and mind blanking, we see smaller pupil size as compared to on task, which represents a lower level of arousal during these mental states. Moving on, this is an example of how eye movement looks like. So you can see these circles, and these circles corresponds to periods where our gaze was relatively still. So our eye stopped for some moments to consume information, and the size of the circle that you see corresponds to how long that relatively still gaze was there. And this is called as fixation. And the lines that you see between those fixations are called saccades. These are rapid ballistic eye movements that happen. So we looked at average fixation duration per trial, and we saw a reduced visual engagement during mind wandering and mind blanking, because as we can see, there is shorter fixation duration for both the green and the blue one, mind wandering and mind blanking. And for saccade, we looked at saccade rate, which is saccade per unit time. So we see fewer saccades in both mind wandering and mind blanking, which means there is reduced active visual scanning. So if you're reading a sentence, you might not be looking at all the words in mind wandering and mind blanking. Moving on, to answer the first question, yes, on task shows faster reading, fewer errors, longer fixations, larger pupils, higher saccades, which means there is stronger engagement. And mind blanking also shows shorter fixations, smaller pupils, fewer saccades, and overall a deeper disengagement from the task. Hence, we can argue that mind wandering and mind blanking should be considered separately. Now let us move on to the second question. Can eye movements reliably distinguish these states? So, as I mentioned before, it has been attempted previously, the mind wandering classification. So we basically tried to methodologically replicate one of the paper, which was Faber et al.'s automatic detection of mind wandering. But there were certain key differences which I would like to point. So they only used the reading task, whereas we used the reading as well as a go-no-go task. They only had 2 mental states, on task and off task. Off task including only mind wandering. We had 3, mind wandering, mind blanking, and OT on task. The probe was self-caught. Now what is a self-caught probe? So imagine you're reading a sentence and you suddenly realize, oh, I was mind wandering. So you just press a button and that gets recorded. Whereas a probe-caught method which we used was, so while we are designing the experiment, we add those probe after a certain amount of trials. So that was 3 key differences. And then we started our work with basically trying to replicate the best performing model of their paper. Before that, let me take you through some pre-processing steps. So first we just merged the sample fixation and saccade events. Then we extracted 4, 6, 8, and 10 seconds windows prior to the probe. So if you remember the probe that we saw, and if someone pressed 1, that means they were on task, we would take the prior 4 seconds of data, or 6 seconds, 8 and 10. So we created this 4 windows to see whether the time windows can actually influence the classification. Which time window has the best classification, shorter one or the larger one. Then we also computed summary statistics. So probe, then we took 4 seconds prior, and then we calculated, let's say, fixation duration. So we calculated mean, median to capture the nature of the distribution. Then we also did some interpolation because there was heavy class imbalance. So out of all the probes, only 21% were reported to be mind wandering and only 6% to be mind blanking. So to get a good model, we had to artificially interpolate the data. And we used the same algorithm used in the Faber paper. Moving on, for the validation, we used leave one participant out approach. So we had 15 participants. We trained on 14 and tested on 1, and we did it for all the folds. Finally, the final pre-processing result looks something like this. So this is a vector, and each number corresponds to a particular feature. So it could be pupil size, saccade amplitude, and so on. And there would be a label. So the label you can see here is mind wandering. Before I show the results, there is one metric that I would like to introduce, which is AUROC. So imagine if I create a model that can classify between cats and dogs. That is trained to identify cats, right? Now, if I present a cat and the model says, well, it is a cat, that is a true positive. But if I present a dog and the model says, this is a cat, this is a false positive. So if you plot all the true positive and false positive for every decision threshold, we get a ROC curve. So if you see the purple line is a perfect classifier. So the true positive rate is very high and the false positive rate is really less. And these are some values. So and we take the area of this curve to get the AUROC value, which is used to evaluate the models. I'll have the legend so we can compare the results. So the first model that we tried was binary logistic regression, which was the best performing model of the Faber et al. Paper. So to adapt it to our study, since they had binary classification, we did mind wandering to be the positive, and then negative was OT plus MB. Similarly, for mind blanking detection, we had mind blanking as the positive class, and similarly, OT and mind wandering as negative. And we tested this 4 time windows, and the benchmark results that we are comparing against is the Faber et al. So you see AUROC score is, the yellow one is 0.64, which means it was a moderate classifier. So the results show it was not very good. We see it was just random. The model was just randomly guessing things, did not learn any classification. But interestingly, for the mind blanking model, we saw much better results. So mind blanking classifier performed better than the mind wandering one. And how I interpret this is that there might be more unique eye signatures in mind blanking as compared to mind wandering, at least for this particular model. Then we thought, well, since we have 3 classes, why not try a multi-class regression? So here we also tried a cross task. So initially we only trained in reading and we tested on reading, but now we trained on reading and we tested on go-no-go. So I would like to bring your attention to these 2 rows. So the first one, you see the task was trained on go-no-go and tested on go-no-go. So this is the same task example. And here we see the score was 0.59, moderate. Whereas when we tested on, trained on reading and tested on go-no-go, we saw a result of 0.62, which means there are some generalizable eye metrics which are independent of the task, as observed in the cross-task transfer, which can actually outperform the same task results as we see in the go-no-go. Moving on, we thought, well, there might be some non-linear relationship in the model which are not getting captured by the previous model. So we thought, let us try a multi-class random forest. And here, we saw the best results for the reading and reading. We saw 0.74 AUROC, which is a good classifier. And interestingly, we saw that reading task consistently outperformed the go-no-go task, which means for classification, the task that we are using has some importance. And how we interpreted this was there is just more dynamics in reading. So when you're reading a sentence, you have to move your eyes across different words. But whereas if you, for a go-no-go task, you just have to press the button as fast as possible. So the dynamics are not captured as well in go-no-go, and which is why we think reading consistently outperformed go-no-go. Finally, we looked at the best features across all the models. So we see some patterns. We see that pupil metrics and the gaze metrics were common across both the tasks. But there were also some unique, so reading we saw fixations were more important, whereas for go-no-go we saw saccades are more important. So based on the task, the kind of eye metrics that predict mental state are also changing, but at the same time there are some generalizable eye metrics which are constant across both the tasks. So finally, can eye movement reliably distinguish these states? The answer is yes. And are these distinct eye movements pattern for each mental state? Does the two tasks exhibit distinct eye movements? The answer is also yes. As we saw that reading relies more on fixation and go-no-go relies more on saccades. And are there shared eye movement patterns? The answer is also yes. So features like gaze variability and pupil size metrics were found that they were common across both the tasks, which means in principle, a real-time classification of this mental state is actually possible. And this was the final summary. So these mental states are distinct, they can be classified, and there are generalizable as well as distinct metrics. So maybe if we want to create a mental state classifier to fit into a car, then we have to find a task which captures the richness of eye movements the most. I think that can be the best way to capture mental states through eye movements. Some limitations, so we collected data for 16 participants, but were only able to use for 15 because of technical limitations. So we are planning to collect more data, and maybe we can also explore much more complex models. Thank you so much. I would like to thank my supervisors, Sumita sir, Samar sir, and Sumit sir for guiding me. And also this is my first time presenting at a conference. So thank you to all the organizers, and a special shout out to my friends Rashmi and Prishti. Thank you. Any questions or thoughts? A lot of questions, okay.
Okay, so I had few questions about the method itself.
Yeah.
So generally in mind-wandering probes, they are given at an unpredictable time, right? So, but you used every 30 seconds. Was there any specific reason?
Not particularly. I mean, it was given after every 30 seconds for the go-no-go task. For the reading trial, it was around after every 4 to 5 trials.
But would that introduce any confound?
Possibly. I mean, possibly, yeah. That could be a confound.
Okay. So a second question that I had was about the mind blanking thing. So
Yes.
how does your probe differentiate between a situation where I don't remember what I was wondering about versus the mind was actually blank?
So mind wandering is not necessarily unconscious in the sense that you don't remember.
No,
Sorry.
Mind blanking, right?
Yeah, mind blanking is not necessarily unconscious. So you
no,
don't have any mental contents, but you are still aware that you did not have any.
So let us say I had mind wandering episode, but
mind wandering or mind blanking?
mind wandering, let us say, okay?
Yeah.
Right, but when you are asking for a probe, you would ask for the content to differentiate between, because you didn't present the probe itself. So we don't know how you are differentiating between mind blanking and wandering.
Actually, I think so. The probe was actually presented. So the first slide that you saw.
So what instructions did the participants had?
So it was basically you have to just. So the table that I showed was actually presented to the participant. This one. So you'll see this after a trial, and it says in the previous trial. So at that moment, where was your mind? So if you're thinking or something else, if you press 2, that would be mind wandering. And if you say blank or not focused on anything, that is mind blanking.
Okay, sure.
I hope I've answered
Sure.
it. Okay, thank you.
Yeah, so let me take it up with mind blanking because I find that more fascinating. So the issue is this, right? A couple of things. One here, they're not focused on anything. What does it mean?
So this is
when
just
I remember, a lot of people think when they are mind wandering, they are not focused on anything.
Yeah, so
there are kind of two kinds of mind wandering, right? At least some people like Selly and all have made this distinction that there can be intentional mind wandering versus unintentional mind wandering. Where intentional mind wandering, you have like you're planning for tomorrow, is considered intentional mind wandering. If you sort of drift off, now the question is that a lot of times when people drift off mind wandering, let's uselessly call that, they will interpret it as not focused on anything. And so they will actually say, because the problem is you have an or there, blank or not focused on anything.
Yeah.
So it leads to an interpretation when they are not sure, they are actually thinking about something a bit drifted off, they would go for mind blanking, but it may or may not be mind blanking.
Yeah, that is a valid concern. For this project, the operational definition of mind wandering is thoughts that are not under any particular schema. So the planning would not be mind wandering.
Thinking of something else is mind wandering. So in that in that classification, intentional mind wandering will go into 2.
Yeah.
Unintentional mind wandering will get into 3.
Yeah, I mean, I can see that, but this was to...
You may disagree with that classification, I have no problem.
Yeah. But for the blanking thing, we can't give an operational definition to the participant. It has to be simplified. I think that is why some meaning got lost while you were trying to simplify it for the participants. But I can see the not focus on anything can be an issue.
The other is related to results versus measures. You have only a very small number. If you can go to results, I was just a bit puzzled. Just go to Saccard results comparing mind wandering and mind blanking. You had these bar charts. Yeah. So, for example, Saccard, you do say that mind blanking is significantly different with 3 stars. I mean, the bars look so close visually.
Yeah.
I simply can't believe it, to be honest.
Yeah. So since there was heavy class imbalance, we used linear mixed effect model for the analysis. But to visualize it, these are the mean plots. So the effects are not really reflective in that way. So we used LM models for the significance. But the plots are mean plots, which is why it looks a bit different here.
Yeah, but I don't see the difference
The
at
error bars
all.
are standard deviation.
Yeah, but okay. So yeah, it's sort of because, for example, where you see visually speaking a larger difference in fixation, you actually don't get a difference between mind wandering and mind blanking.
Yeah.
So there is. I'm just the other issue is that because you have such a small number of trials, right? You have only 6% of trials. 6.6. How many probes are there for a particular subject?
There are 32 probes.
Out of 32 probes, only 6% were mind blanking probe, right? So 6% of 32 is 2 probes at best. And any Saccard calculation you're doing is an average of just 2 trials. Is that a reliable estimate? That's the other thing I was wondering. When can one really trust this? With just really 2 trials, taking a mean of Saccardic reaction time, for example.
Yeah, I mean the sample size is less, but I would argue that pooling it across participants might give us some power, but yeah, still I can understand.
A quick question. In the classification, you said interpolation. Basically, how did you do class balance?
So we use the synthetic minority oversampling technique, the SMOT algorithm.
Minority, so you repeat the
so we found
fewer
the nearest
samples. Right.
nearest neighbors and then plotted a line and then data points across that line.
Yeah. Okay.
Hi.
Hello.
Nice study. So I'm wondering that you have this classification, and your classification accuracy is not very great, which is like 0.74 or something. So did you try, so you only tested on eye tracker data, right?
Yes.
All the eye tracker parameters. Did you include behavioral parameters also in the model? I mean, did you try separately behavioral parameters, separately eye tracker parameters, and the poolings, some of the behavioral parameters with eye tracker parameters to see whether it is improving the accuracy of your model? Did you try that?
Yeah. So the issue with that is, since we were also planning to do cross task to see how these generalize across task. So such as no-go error would have no implication for the reading task, which is why we skipped over the behavioral metrics and only looked at the common eye metrics between the 2 tasks.
But are you planning to
We can look at it. Yeah,
try?
sure.
Yeah.
We can look at it.
And the second, it just extension what Professor Narayana Srinivasan asked. Like you have, I mean, you have tested 4 second, 6 second, 10 seconds. Why not like in general? I mean, even one of your posters also, I mean, the same group, I asked and like, I think she took 6 seconds, you know. So I'm just wondering why this, I mean, why not just take the whole, you know? I mean, do you believe that this mind wandering or mind blanking started? I mean, yes, I agree that I mean, when you start the experiment, maybe it's mind wandering is not happening immediately.
Yeah.
It will take some time, but why not just take the whole? So you can increase the, you know, trial number and you have more power.
Yeah, so actually the benchmark result that I showed was for 12 seconds and our longest window was 10 seconds. And the reason for that was just a technical reason. So we had a go-no-go task, which is a very short duration task. So when we try to pool the prior results, it actually overlaps with the other probes and that caused a lot of technical problems. So because of that, our study, because we had go-no-go, which was a shorter duration, we had to make some adjustment and we couldn't go beyond 10 seconds.
Thank you.
Thank you so much.
Okay, I think there are more questions, but the lunch is getting delayed, so let's thank all the speakers of the session. Thank you.
Thank you, Professor Krishna sir, for chairing this session. And now we break for lunch and we get back at 1:45 p.m. sharp. I request all the presenters who have the presentations in the next in the next session, please come over to the stage and check, get your PPTs checked. So I call out their names. Arijit, Aditi and Harish, kindly come to the stage and get your presentations checked, please, for a smooth section. Thank you. You. And all those who have poster session today, please go and put up your posters in the lunch break itself so that you don't miss the oral session. So we are still waiting for Arijit and Harish. Ashoka University. Okay, Arijit, go there. Harish Sinai from AITD. So just checking if the speakers for this session are here. Arijit? Okay. Aditi Jha? And Harish? All right. So welcome back, everyone. Now we move on into the next session, which is the last oral session, and it's going to be very interesting. It's on music, motivation, and cognition. And I request Dr. Jay to kindly chair this session, Professor CBCS. Thank you.
So first we are having Arijit Bhattacharya from Ashoka University. He will be talking about music, mood and mind, functional modeling of structure, state and trait-based modulation of emotion.
This is not working. Can you come? Hello and very good afternoon to everyone. This is Arijit Bhattacharya, a PhD student at Ashoka University and a global scholar at the University of Oxford. I'm going to present a part of my PhD thesis, which is looking into the music, mood and mind by functionally modeling structure of music, behavioral response of participants, and the personality trait of the participants. Behind the project, we have a guiding philosophy of our lab that cognition is not something just driven by the external stimulus, but it's also an interaction between the external stimuli and the internal evolution of ourselves. And to study that, what can be a better option than emotion, one of the most complex cognitive phenomena that we have. And when it comes to different stimulus for understanding emotion, music stands out as one of the most predominant stimulus because of its dynamic nature and the complexities. Different cognitive scientists have argued that cognition is not two-dimensional, and I completely agree with them. But to study it, Russell have made our work much easier by doing a dimension reduction technique and making a circumplex model to understand emotion in two dimensions of valence and arousal, where he showed us that valence is the x-coordinate ranging from something positive to negative, or in common terms, happy to sad, and valence is the intensity of the emotion starting from exciting to relaxing or active to passive. Jocelyn has given a very good definition why music can be used as emotional stimuli, because they mentioned from a bunch of similar studies that one of the most common goal of musical experience is to evoke emotion or influence emotion. People use it for their day-to-day context. It's one of the naturalistic stimuli that many people use every day. So it does not make a difference from a naturalistic stimuli like others, but music stands out as a most predominant stimulus because of its lesser context dependence on semantic or cultural constraint when not added with any lyrics. So here we chose music in our study. Many studies have demonstrated two types of effect of music, one driven by the structure itself, such as the complexity of music, the beat onset, note onset density, beats per minute, and even the pitch that deviates across time. Whereas the other school of thought believes that it's mostly our internal state, such as the mood, the anxiety, and other state like age, that can influence the perceived emotion. So what my question is it the structure of music alone that influences the perceived emotion, or is it the internal state, or is there some complex interaction happening between both of them continuously? Now to do that, I selected a bunch of musical stimulus from a validated Indian classical music battery created by Dr. Nandini Chatterjee Singh and Dr. Avantika Mathur at the National Brain Research Center. I picked up 3 music. Each 3 of them are different in terms of the note combination. One has sort of more major note, or which we call Shuddha note, or the pure tones. And another music has a dominance, equal dominance of both Komal note, which is the half semitone, and the pure tones. And another music has all Shuddha note, and one dominant komal note. So they're different in terms of their notes. And inside the music, we have two segments. In Indian classical music, we call it alap and gat. To tell it scientifically, one is rhythmic and one is arrhythmic segment, which we can see that we have different combinations of stimulus. Although we always follow a alap and then a gat to make it more naturalistic while doing the experiment. We conducted our experiment at Ashoka University with so far the number of participants of 34, and we performed our experiment through PsychoPy with a continuous rating of emotion using a joystick. This is how my experimental design looks like. We have silence followed by a music and then another silence, and like that it goes on for around half an hour, where the musics are kind of randomly ordered, so they are not fixed. Someone can get music 2 before music 1, someone can get music 1 in the second place, so it's completely random. And we give the instruction to the participants from the moment they see the circle, even if there is no music, they can start rating whatever they're feeling, and they can continue rating the same or whatever they're feeling at that exit time point throughout the experimental paradigm. What we get is something like this, a complex circumplex domain data and a time series data. I'm not sure if it is visible clearly, but the time series data, the time series data shows a huge variations in participants' rating for the same music. So to make it simpler first, I tried understanding a dwell time of each musical stimulus inside the circle segment, and to understand if it is something, a random association, or is there something significant effect based on that. So to say it little informally, that does music have a home inside this circle model? What we find some interesting pattern, if you look at all three circles in the top, they are mostly rated on the bottom part of the circle, and they all signifies the arrhythmic phrase of the music. And the next, the below three are the rhythmic segment. Although they are in the below part or the bottom part of the circle, they have also reached the top part of the circle as well. To look at the valence, now just look at the first row, and we can see that it's mostly on the left side of the circle, which is the most sadder dimension. For the second one, it's mostly on the right side of the circle, which is the happier dimension. For the third music, however, it's different. For the top one, it's mostly on the sadder part in the left side, although on the neutral coordinate a little bit, but for the below one, it's mostly on the righter side. So I did a simple binomial test to understand if it is just a random association or is there significance. And we find out kind of a similar result based on literature, that which are the alap segment should signify something arrhythmic, and the gut segment should be something rhythmic and will be more aroused, and alap should be lesser aroused. And similarly, if there is more minor note or more komal note, that should be sad in the emotion. More shuddha note or more major note should be happier in the dimension. But there are more complex result we have in the time series data. So we designed a functional data analysis based on our time series data, where we first modeled our joystick data, smoothened it to remove any jittery data from the joystick, and then used a functional principal component analysis, and followed by clustering and regression, using both linear regression model for functional on scalar, and as well as something called concurrent functional regression with linear mixed effect model. So this is how I modeled it first, removing the jittery noise by doing Gaussian filter and smoothing the data over time. And after that, I expanded my data using basis expansion into 20 such data points. We got 20 bases for each participant, and then computed a covariance matrix, such as how much each of the basis function varies from each other, and then finding a global pattern which represent kind of the group level of all the participants with a 90% variability. We found total 9 such pattern, which are the 9 eigenfunctions, which explains the group level variability of the participants. And from that, we got for each participant 9 principal components. So this one we have represented in a 2-dimensional image, but it's actually a complex 9-dimensional image where each participant exists in a 9-dimensional space with independent values for their principal component. Based on that, we did K-means clustering, where we tried to understand if we can find significant groups with the similar patterns. And I also tried reconstructing the mean of the structure of the participants' rating from the principal component analysis, and we can see that each three of them are, each three clusters significantly, they're kind of different from each other, they're not same. After that, we came up with this model of function on scalar regression, where we wanted to model our time series data and understand how much the scalar variables, such as the top-down feature, the age, the mood score, they impact on the time series pattern. What we found is for music 2, which is so-called a happy raga or Hamswadhani based on the circle model or even the previous literature, we found that state anxiety and engagement of music have significantly clustered with it. And we found that higher anxiety and higher depression have completely altered the principal component 2, which is the secondary dominant pattern of a behavioral rating. Whereas when we move to music 3, which is Rag Desh, and for which we had a kind of different ratings in Alap and Gat, we found that most of the trait score like depression inventory and then trait anxiety and even higher neuroticism, it have also altered the primary curve for the functional data. And we have found that positive mood have made it higher, which means the people or the participants who have lower mood, they feel lesser aroused for that music than the other participants. We found an interesting effect for age. Interestingly, the people who are at higher age, they have a different baseline trajectory for the musical rating than the people who are at the lower age. And it has a huge beta, so it's clearly different from each other. Now, we went to a little bit more complex understanding of it. So we did a concurrent functional regression with the linear mixed effect model, where now we have, along with the scalar predictor, we have a functional data, that is music itself, because music is also a time varying factor. So we first decomposed the music spectra with Librosa and tried getting beats per minute, note onset density, spectral features, spectral flux, all structural features of music, and tried to understand if they are also impacting the participants' rating. What we found is that for arousal, most of the musical structure had a significant beta value and the T value, which suggests that music do influence our perceived arousal, which also goes with the existing literature. But when it comes to valence, we found that we have also additionally have the effect of the trait measures such as neuroticism, trait anxiety, and even the positive mood. So they have also found to impact the perceived valence. So we can have an understanding from it. So maybe we feel the intensity of the emotion through the structure of music, say when it's very rhythmic, too much beat going on versus arrhythmic and very relaxing, which we say. And we kind of understand or interpret whether it's happy or sad with an interaction or an effect along with the top-down features such as our mood or anxiety. With that, I also tried understanding, does a previously listened music impact the next music's perceived emotion, which we can also call as emotional spillover or a priming effect for music. To do that, I created a simple linear mixed effect model where I first calculated each music's baseline rating when they were presented at the first block of the sequence, and then tried to calculate a deviation of that when they were presented in a different block, and understanding if that deviation has some effect from the previously perceived music. Now again, this is not the full model that we are doing. We are doing more than this, and I'm yet to get more results for this, and then I hope I'll be coming back with that. So to conclude, we found that higher state anxiety and depression may impact the secondary dominant pattern of the valence or the pleasantness, and the anxiety trait, depression, along with neuroticism might impact the magnitude of the arousal, which is the principal component 1. We have also found that age is one of the strongest predictor, and higher valence at the previous end of the preceding music can impact the next upcoming music. There is no such spillover effect found in terms of arousal. It's only there for valence. I mean, we can try to understand implication of this in a clinical settings as well in terms of music therapy, a similar type of setup. First, that a happy raga is not universally happy. Everyone perceives it differently. and there are more than music that plays a role into it. Our internal state, our mood, cultural context, everything plays a role into it. And we have also found that for higher anxiety and depression score, pleasantness is kind of distorted. So therapies might want to account for that. Now this is all behavioral. We wanted to connect the dot neurochemically and understand how our brain's neurochemistry change over time. So we designed a functional MR spectroscopy study where we did the similar experiment when a participant is inside a functional MR scanner and understanding how dynamically the molecular behavior also changed along with music. We did a single voxel MR study. I'm yet to get the result and come up with this. But I hope in the next ACCS I'll be able to come up with the understanding of neurochemistry of the brain for our perceived emotion. With this, I would like to thank my guide, Dr. Dipanjan Rai, our collaborator Momita Das, and intern in the lab Krutika for helping me out of the project. Thank you.
Question.
Yeah.
I didn't understand something. I didn't understand how PC2 is arousal. How did you determine that?
So we did so we had these valence and arousal ratings.
Okay.
Here,
so they
you
have
yes,
ratings for
yes,
both.
Yes,
I see,
yes,
I see.
separately.
Sorry.
Yeah.
Hello. May I ask, you used any platform for getting this PCA and all this?
Simple Python and R.
Python.
Yeah.
Yes, Python and Anaconda.
Yes, yes.
And how was your data? Like it was in a tabular format, CSV format. Which format it was?
CSV.
CSV
Yes,
format.
yes.
Okay, so it was mostly tabular, and from
Yeah.
joystick only you took the data.
Yes, we get a sampling rate at around each 0.05 millisecond, and then we get a time series data like that.
Thank you.
Hi.
Hi, sir.
Thanks. I was just wondering, is there any way to interpret your principal components? It's nice that you can
That's what I'm
do regression
trying.
and use it statistically, but is there a psychological or a cognitive interpretation of these components? Otherwise, exactly what are we understanding here?
Yeah, I agree with you. The first principal component is mostly the global pattern, how everyone rates. And the second one is how the subtle changes happen in the rating. So something more local, I'm assuming, with that. But I think we need to look more extensively into the modeling part to understand what is that local phenomena maybe.
No, one possibility is that you could empirically, I'm not sure, but you could empirically manipulate by removing the, say, the second principal component and then reconstructing what you have and then now see what that audio, whatever that is, elicits a particular emotion, right?
Absolutely.
At least that's empirically feasible.
Yes, yes. We can do that. Right now, I only did for PC1 and PC2. We can do for all of them and combine them all as well. Yeah.
Okay, thank you, Arijit.
Question. So the stimulus that you said were different on the basis of note.
Yeah.
Right. That was the only difference.
No.
That put them apart, or
So
there was
one
more?
thing is the note that each music is different from like 1, 2, 3. They are different in note.
Yes.
A and B are different in the rhythmic complexity. So A is arrhythmic, B is rhythmic. So B has a fixed pattern of rhythm, much more higher than A. So other things are controlled in the stimulus.
That's all.
I have a small comment on that. Like most of the Indian ragas are based on like they are logged with some time. It's a daytime, morning time, evening time, night time. So I think you haven't considered that, like playing a night raga in the afternoon or the morning.
So three of them mostly comes, all three of them mostly comes in the time of afternoon to evening. And I don't think we are going to do experiment in the nights. Most of the data are collected in the afternoon to evening. So we have controlled for that as well. So timing does not have an effect in this.
Thank you, Arijit.
Thank you, sir.
I think I can move to the next participant. So next is Aditi Jha from IIT Gandhinagar. She will be talking on neural coding of auditory feature during music perception and imagery.
Thank you for the introduction, sir. Hello, everyone. Good afternoon. I am Aditi. I come from the Department of Cognitive and Brain Sciences, IIT Gandhinagar. And today I'm here to talk about my work on feature-dependent cortical representations during music, imagery, and perception. Since my work is going to be revolving a lot around music cognition, it only makes sense that I begin my talk explaining the foundations of auditory neuroscience. So we all know that we listen to sounds via our ear. So once a sound reaches our external ear and then goes to our middle ear, it reaches a spot called the cochlea. The hair cells in the cochlea are what are actually responsible for the sound transduction. The auditory information then moves on via the auditory nerve to the brainstem, midbrain, thalamus, and is then finally projected to the primary auditory cortex, as we will discuss later. Speaking of cortex, it is also important to understand the cortical tonotopy in auditory cortex. What you see here on the screen is a brief pictorial representation of the auditory cortex. So the area you see in green is called as the Herschel gyri, or the primary auditory cortex, or A1, as we'll be referring to throughout the presentation. This area is the first cortical stage of auditory processing. This is located on the superior temporal plane, and it is this area which is responsible for most of the tonotopic sound processing in the brain. This area encodes all the pure frequencies and spectral detail. The second important area for our presentation is the superior temporal gyrus, or the area represented in red. This area is responsible for more of the higher order integrative processing, and it processes all the complex properties of sound, such as phonological patterns, harmonic representations, auditory objects, etc. Now, one of the easier ways to understand auditory signals is to break it down into multiple auditory features. This here is my attempt to explain the classification of auditory features and then to explain my rationale of selecting these features. Now, auditory features could either be symbolic or non-symbolic, depending on whether their representation comes with an explicit musical meaning, or whether they are purely acoustic or perceptual in nature. These features also can vary from being low level to high level, depending on how they are derived. So low level features are derived entirely from the waveform. They are entirely perceptual. Whereas as we move on to the high level features, we see the features becoming more abstract, more symbolic, and more culturally defined. Now, the two features I am going to be using for the case of my study are the spectral features as well as the chroma vector, or the chromogram, as we are going to call it. I would like to take you through the basics of the features essentially, and the first feature I am going to be talking about is the Mel frequency cepstral component. These components are derived from the Mel frequency cepstrum. Now, what is the Mel frequency cepstrum? Simply speaking, it is the non-linear transformation of an audio signal's frequency content. And why do we need to use it? We need to use it because their perceptual basis makes them much superior to linear spectra, especially for human perception-like tasks. If you look at the picture on your right, you see a direct comparison between a frequency domain spectrogram and a cepstral domain spectrogram represented on the Mel scale. The difference between the two spectrograms with similar activations is obviously the scale. And the reason why people use the Mel scale is because it's a good approximation of how humans perceive the nonlinearity in pitch. MFCCs have been used widely to study speech parsing, sound categorization, and other auditory effects. The second feature I am going to be talking about is chromogram. Chromogram, simply speaking, is the perceptually motivated representation of an audio signal's pitch content. What it means is, a chroma essentially abstracts away all the pitch height and just classifies an auditory signal on the basis of the 12 pitch classes. What are these pitch classes? These pitch classes are the 12 semitones of equally tempered Western scale. So the 12 notes you see on the screen here are the 12 pitch classes into which the chroma features are divided. why is it important to use chroma features? Is because chroma features are absolutely robust to any octave transpositions, any timbre variations, and any instrument changes, which essentially means that a combination of notes played in two different instruments in two different octaves will have a similar, will have the same chroma feature representations. And another reason another reason why it becomes important to look at chroma features is because previous research has highlighted that humans process humans process the pitch classes in addition to the musical height as well as the instrument changes. Chroma sees a lot of applications across information retrieval, auditory analysis, and musicology. Now, the two processes I'm going to be looking at through my work is music imagery and perception. Now, music perception, as we all know, is a bottom-up process driven by an external auditory stimuli. What happens in music imagery, though, is that it's an internal generation of musical sound without the presence of any auditory input. And research time and again has displayed that music imagery often involves the reactivation of the same perceptual traces as auditory and sensory motor cortices. Now, coming to the research questions I am planning to answer via my research, the first question I'm planning to answer is how do distinct musical features shape cortical representations across the auditory hierarchy? And the subsequent question to that is, do spectral and harmonic features, here represented by MFCC and chroma, recruit distinct neural pathway during music imagery and perception? To achieve the same, our work essentially relies on openly available fMRI datasets, and the first dataset we use is a music imagery dataset compiled by Zhang et al. This is a dataset for two different conditions, music perception and imagery, and the perception condition was essentially a free listening recording on the first movement of Beethoven's Symphony 9. For music imagery, Zhang et al. Animated the musical piece through Stephen Malinkowski's music animation machine, and the participants were made to undergo a number of practice trials looking at the visualization as well as listening to the sounds. All of these participants were musically trained individuals, so when they were confident that they could imagine the sounds by looking at the visualization themselves, the imagery trial then included them just looking at the visual cues and imagining the sound in the head. The second dataset we extended the study on is curated by Nakai et al. This is a dataset of music perception alone, and this involves participants listening to music across 10 different genres of music. One of my major goals through my study is to map the auditory features to the brain activity, and how I do the same is by taking the auditory stimuli and extracting features from it using the music information retrieval system. And the features we've selected for this analysis are MFCC and chroma. We pre-process the fMRI data using a pipeline which involves motion correction, slice time adjustment, spatial normalization, and smoothing. And then we use these extracted features as a regressor for the general linear modeling that we do on the extracted fMRI data using statistical parameter mapping in MATLAB. Now, I'll briefly take you through the results of both of my studies, and we'll discuss the observations and the inferences that could be made using them. The first result over here is for the feature-specific activations in music perception. I've tried to segregate the common and the unique activations for both the features using some image processing. So here we do see that the activation for perception is mostly centered around the auditory regions, specifically both primary as well as secondary auditory cortex. And while chroma has more localized activations here, the MFCC activations are more widespread across the entire superior temporal gyrus. If we look at the same result for music imagery, we see that imagery recruits a widespread activation across the associative cortex, especially associated with chroma features. Again, both MFCC and chroma do see some common activations in the superior temporal gyrus, but we find any activations missing for the Herschel gyri. If we just compare for the MFCC activations for both music imagery and perception, we see that the activations are very sparse and are very sparse for music imagery, versus perception shows very strong activations in both the Herschel gyri as well as the auditory belt. Again, if you look at the chroma activations for both perception and imagery, we see that the imagery activations are concentrated in occipital, parietal, and angular regions, whereas the perception activations are localized in STD and auditory belt. Now, if we look at these results quantitatively, one of the first observations we find are regarding the activations in the temporal cortex. Do we see a pattern here? The results essentially say that during music imagery, the primary auditory cortex activation is almost negligent. This leads to believe that imagery does rely on top-down reconstruction, and this suggests that imagery probably only engages higher order auditory and associative areas. These results are in line with the findings of Zatorre and Halpern. Another observation we find when we only look at the music imagery results is that the activations due to chroma in both left and right hemisphere are higher than MFCC activations for occipital regions, parietal regions, and for angular gyrus regions. This probably shows a link of music imagery to music-based reconstruction of musical pitch structure. Coming to my results for my second study, we again look at the feature-specific activations in music perception, and we see that both MFCC and chroma have localized activations in bilateral STG, but the MFCC activations are stronger in both primary and secondary cortex. To look at a more quantified representation of the same, we have tried to quantify the activation within the auditory cortex for music perception, and if you look at it, we see that the major amount of activation is associated with the MFCC feature, and in both primary as well as auditory cortex. And if we look a little closer, we also see that chroma activations are weaker in the primary auditory cortex and are only moderately present in the secondary auditory cortex, or the STG as we say. So to summarize my entire work, I would like to give you a few key takeaways from my presentation. The first key takeaway is that we found minimal primary auditory cortex during music imagery, there was close to no activation in the Herschel gyri, and contrasting to strong responses during music perception. The second takeaway we have is that harmonic features like chroma uniquely activates occipital and parietal regions bilaterally during music imagery. Coming to music perception, we also saw that MFCCs elicit widespread primary as well as auditory cortex activations during music perception, in contrast to the lack of activations associated with the chroma features. One consistent takeaway we have throughout the presentation is the importance of the superior temporal gyrus for both music perception as well as imagery. STG overlap was seen across different features and across different conditions, again reinstating the importance of this particular region for auditory perception. Now, this work is part of my ongoing doctoral work at IIT Gandhinagar, and I would like to take this forward by extending it to multiple features beyond just MFCC and chroma, and I would like to explore more melodic rhythmic features. I would also like to test the hierarchical auditory processing with multi-level encoding, and I wish to expand this work onto more multimodal, onto different modalities. I'm also open to exploring the applications of this work in cognition, musicology, rehabilitation, etc. As I said, this work is done as part of my doctoral work at Brain and Informatics Lab, and I would like to thank my supervisor, Professor Krishna Miyapuram, my collaborator and mentor, Professor Derek Lomas, the cohort of researchers I have at IIT Gandhinagar, and to Playpar Labs and FICCI for the consistent support they've had for this project. Thank you so much. I would be open to taking questions.
Thank you, Aditi. Question?
Okay, let me ask. So I was wondering whether you had access to any kind of self-report or behavioral data during either music perception or especially mental imagery.
No, sir, we did not. I think...
For example, I would be curious to know that when they imagine the music, say Beethoven's Ninth Symphony, first movement, are they actually visually also simultaneously imagining their favorite concert performance that they saw, for example?
Yeah.
That would explain why visual regions get activated, right?
Yes, sir. So I agree that's a very good point, but unfortunately we did not have access to any such behavioral ratings. The only confirmation we had was that participants were able to imagine the music after the number of practice trials they had.
But what did they imagine?
So how this works is that I could not play the video here, but...
No. I'm just wondering what exactly they imagined.
Okay. So they were visually cued to imagine the similar symphony as what they heard in the audio-visual practice trials. And they were asked to just look at the visual cues and imagine the same symphony while they were being recorded.
No, but after they imagined, there must have been some validation or questions about what exactly they imagined. No? There is no self-report or phenomenological or any kind of experiential data.
No, I agree, sir, but in my information, the data set we used did not provide us with any self-reports. But I would keep this in mind while curating a data set in future.
Hi, am I audible?
Yeah.
So maybe I missed it, but can you elaborate more on the statistical analysis of the fMRI activation? Like specifically, it's not very clear to me whether they use it as a parametric modulator, whether you there's a multicollinearity, do you orthogonalize them, or what is the statistical thresholding and multiple comparison or all this, the image that you showed of the activation of red and blue thing.
Okay. So it's probably an oversight, but we did make a general linear model for the fMRI datasets, and for both the general linear models, we used the MFCC and chroma features as regressors. And then once we had the results for individual participants, we did do a group level analysis, with a p-value of less than 1%. And these results that you see here are actually an image processed version of me. I essentially did image processing on the result maps to then see whether there is overlap between the MFCC activations and the chroma activations, and then subsequently whether there's an overlap between imagery activations and perception activations.
It's not very clear to me, but I can discuss with you offline.
We can take that offline.
Okay, thank you, Aditi.
I think there's one more question.
Thank you. That was a great presentation.
Thank you.
I was just wondering about the visual activity in the imagery condition, because the task is visually cued, right?
Yes.
So how do we know that the activation is because of the imagery and not the cueing itself?
No, that's a very good point, and that is also something that we realize that, again, when we have a data set in future, we need to have a visual baseline as well. But what is interesting to me is that the visual area activity, as we talk about, is only significantly higher for one condition and not the other. So if this activity was only corresponding to the visual cues that the participants were seeing, a similar amount of activity would have been seen for both MFCC and chroma conditions. But the fact that this activity is much higher in corresponding to chroma probably tells us that chroma has some role in activating the visual and visuomotor regions. Am I making sense?
Okay.
Okay.
Yeah.
Thank you.
Okay, thanks, Aditi.
Thank you, sir.
Next, Harish from AITD will talk about understanding consumer attention and EEG study on visual appeal and taste of food.
Good afternoon, everyone. My name is Harish Velinkar. I am from Goa. I'm an assistant professor in Agnel Institute of Technology and Design, Goa. And I'm also a part-time research scholar at DSATM, Bangalore. My topic of presentation is understanding consumer attention and EEG study on visual appeal and taste of food. And my co-authors are my guides, Dr. Rupa Kulkarni and Dr. Prashant Patwardhan. I'll just skip the outline of the presentation. So we all like to eat food, and food basically has two main aspects. One is the taste, right? And there are 5 basic kinds of taste. That is sweet, sour, salty, bitter, and umami. And the other aspect of food is the way in which it is presented, like the way it looks. So this includes its texture, the way it is packaged, the colors, and so on. So we are aiming to study how the taste of food and the packaging that it comes in works together to influence the consumer behavior. Right, so see, when we go to a shop and we see a bunch of potato chips or wafers, we always go and pick the flavor of our choice. That is because there is any repeated exposure to a specific flavor conditions the brain to associate it with a predictable taste reward, and that leads to a preference buying from that particular. So that leads to a preference-based buying from the buyer. So if the same food was probably looking something like this or pale in color, then the appetite that we create towards that food would not be as much. So I have particularly, and also, so this is a part of flavor engineering where they never mention exactly what kind of ingredients are that are listed. It is shown as a flavoring agent, and that is the flavoring agent that creates the texture and the dopamine effect, which leads to, you know, us wanting to eat that food. So why I've put a packet of chips is because I'm working on a specific product of PepsiCo, which we all know as Lay's, and a particular flavor of Lay's, that is the Indian Magic Masala, which is known to be the highest selling in India, followed by your cream and onion and other flavors. So we are trying to compare the taste, we are trying to compare if the subjects can recall the taste by looking at the packaging and compare it with the unbranded potato wafers that you get at local shops. So just to brief you about the existing research, see, there is a lot of existing research on simplex taste, that is salt, sour, sweet, bitter, and umami. But the complex food profiles which are available mostly in you know, all these packaged branded chips and savory snacks, this has not been this has been overlooked. And the studies combining taste and visual aspect of such kind of foods have been studied less. Also, most of the EEG studies, they utilize a small sample size, and that too of a certain demographic. For example, there is a lot of study on Japanese soups or Chinese noodles or different types of wines and chocolates. Okay, but these belong to a specific region, okay, and that limits the scope of that particular study. So just to brief you again about the problem statement, we are looking at junk food, especially the potato chips, how it triggers strong cravings, the visual packaging of those particular products, and how they both are linked to one another. So applications, so I have a few friends who are into manufacturing and packaging of products. These are startups, and what I understand is whenever they need to check for or validate for their product, they will normally call their friends or whoever and do some tasting, okay? They will not send it to a lab or do a professional kind of tasting. So the application could be, you know, improve the packaging strategy or enhance your brand position. You can compare your food product with the available competitors and optimize your marketing campaigns accordingly. We know the parts of the brains, but as per the study or the literature, there are these 5 parts of the brain which are normally related to taste and visual of the visual stimuli of the food. That is the OFC. Then we have the insular cortex, which is the primary gustatory region of processing, visual cortex, amygdala, and the ACC. I would like to acknowledge DST, Department of Science and Technology of Goa, for the funding for, I've worked on the Newphony head caps using the flex cap. It's a 8+2 channel electrode, dry electrodes. So the experimental setup is of 100 participants aging between 20 to 40 years of age. And out of 100, 50 are into the experimental group and 50 are into the control group. The one in the experimental group have been given tasting for the branded potato chips, and they are privy to, I mean, they are given the experience of the brand, the package. And the control group has been given unbranded, unsalted potato wafers. Okay, and so these are the 4 conditions that we are checking. Number 1 is the experimental group who will consume the junk food. The condition 2 is the control group who's tasting the neutral food. The third group the third condition is checking for their packaging. And the 4th is they will view a random package from which they have not tested the food, the particular food product. So it's an 8-minute experiment that I've designed, starting with 2 minutes of baseline, where they are staring into a box which is white in color. Okay, and then there is followed by 2 minutes of tasting, followed by 1 minute of rinsing of the mouth. Then there is 1 minute of viewing of the branded package. Then the next 1 minute is viewing of the any other unrelated package which they have not experienced the food from. And again we end with a baseline where they are staring into the box. So the electrodes, there are only 8 channel, it's 8 channel, so I have used 4 from the frontal region, 2 from the central, 1 parietal and 1 occipital, based on whatever I've read and I've understood that this would give me the optimal results. Participant screening, this is the process, data acquisition, data processing, then the analysis and the result. I started working on this in the beginning of this year. So it took me a lot of time to get the data because I'm working full-time as an assistant professor, so I can work only over the weekends or on my vacations. So I am in the just the foundational stage of the statistical analysis, and I've come here to present so that I can get a feedback which can steer my research. So see, the Newphony software, right, internally generates graphs like this. That's the absolute power band, but you cannot export this data and you cannot use it for independent analysis. So what I've used is they provide a Excel CSV file of the spatial positions, and they have this EEG amplitude index. So these are numbers under each of those spatial positions, right? So what I've done over here is I've taken a mean of the values. Okay, for example, the baseline here last is of 1 minute. So 1 minute, and the sampling rate is 250 hertz, 250 samples in 1 second. So that gives approximately 15,000 points. So I have averaged out this point for each of these scenarios and for all the participants. And what we are looking for is change in the mean values when we are going from baseline to tasting and from again the second rinsing to packaging. Okay, so some of them are random, in some you see some patterns. Visually it is difficult to get these things from the mean. These are some of the electrodes that I've put. What I've conducted, okay, see, these are some of the electrodes, and what I've mentioned here is the percentage change in mean when you're going from one state to another. For example, in FP2, the number 11 there mentions that 11 out of 25 participants have shown a 50% change of the values going from one state to another. Okay, that 44% is the 11 out of 25. So whichever have shown prominent changes, I've just highlighted them over there. The second thing that I've done as of now is the paired t-test. So in the paired t-test, I've checked for 4 conditions, baseline versus tasting. So this will tell me how much change is there in the patterns when the subject is tasting. Second is the tasting and packaging. So here we are checking if there is a taste recall. Then tasting and unrelated packaging, we are making sure that if there is any change, it is only because of the package that they have tasted and not because of any random package. And the last one is package and baseline. So here we are checking with the baseline if just by viewing the package, if there is any change in the patterns. So these are the some of the readings. These are for the top one is for the males and the second one is for the females. So what I've observed is when you go with baseline and tasting, the first column, almost all of them are showing a substantial difference between baseline and tasting amplitudes. When you're going from tasting to packaging, when you're checking tasting and packaging, I've observed a recall in 3 of the electrodes for male and 6 electrodes in female. What I believe is males and female, as per the literature that I've read, have a very different way of retrieving data and of emotional processing. This may be one of the reasons. The third thing is tasting and unrelated packaging. So here, there are 2 electrodes which are still showing the recall. That means even after looking at a random package, the person feels as if he has experienced that taste before. FP1 and O1 in the males, and there are 3 in this. So it might be because there are these parts where they might be related to curiosity or just a random food cue that is creating this effect. And the last is packaging versus baseline. Again, there is a substantial change in the values when you are comparing baseline and packaging. As of now, what I have concluded is the taste and packaging have significantly increased brain activation. In males, FP2, C3 and O1, these are the one that are giving me some results as of now. And 2 electrodes, that is FP1 and O1, they are creating a taste recall even while viewing an unrelated package. So I've just collected the control data set, okay, and we are now going to, I'm trying to compare the data with the unbranded, unflavored chips. And then we are going to do more statistical tests, some topo plots. See, the aim is to create a model that can work across any of the branding or branded food products, okay, where you can evaluate how the taste and packaging influences a consumer behavior. That is the ultimate aim. Yeah, thank you.
Thank you, Harish, for the very spicy talk today. So let's have.
Hi.
So,
unfortunately, this is a message to every student present here that how not to use EEG. Okay? It's very interesting to try and study neuromarketing applications. I will not give a lecture here, but one, you shouldn't use it when movement is involved. Consumption of food is movement. You shouldn't do that. Second, you shouldn't use devices which are not validated. You have no clue what you're doing, so better you learn the technique before being very, enthusiastic about, using a methodology for a particular application.
Okay, thank you, sir.
Hello, this is Shweta.
Yes, ma'am.
Actually, I just wanted to know, you said they have recalled the taste.
Yes.
So how from those electrodes you understood from that amplitude that they have recalled? Like, how you inferred they have recalled the taste? You have seen in different electrodes, there's a table.
Yeah, so... right. So the p-values over here are about the significant level. So what I've inferred is that means that there is a not a substantial change in values between the tasting and packaging. So that's how I've inferred that there is a taste recall. And also subjectively also we had given this, but just to compare it.
Okay, thank you, Harish.
Okay, so that brings us to the end of the oral session for ACCS. Now we have the poster session, last poster session on the second floor, and we meet at 4:15 over here for the industry talk. And after that will be our valedictory ceremony, and tea will be served after that ceremony. So see you in the poster session now.